Welcome to the Sleepless Universe. In this video, we'll explore how the universe was born, from absolute nothingness to the formation of stars, galaxies, and eventually Earth. If you enjoy this kind of calm cosmic content, feel free to leave a like and subscribe. And let me know in the comments, where are you watching from? Now, sit back, relax, and enjoy the journey. Before time itself, what existed before space, time, and even the laws of physics? Imagine, if you can, a condition so pure and essential that it transcends our everyday understanding of existence. This isn't darkness, because darkness requires space to fill. This isn't silence, because silence needs time to flow through. This isn't emptiness, because emptiness implies a container waiting to be filled. What we're contemplating is something far more mysterious and beautiful: the quantum vacuum, the foundational field from which everything we know would eventually emerge. In this primordial state, the very concept of state stretches our language beyond its limits. Here, the four fundamental forces that shape our universe: gravity with its gentle but inexorable pull, electromagnetism painting the colors of atoms and stars, the strong nuclear force binding the hearts of matter together, and the weak nuclear force governing radioactive decay, all existed as one unified, harmonious force. Picture a symphony where all instruments play the same perfect note, creating not cacophony, but a sound so pure it contains within it every possible melody. The temperature in this pre-reality wasn't hot or cold. These concepts require matter to have meaning. Instead, energy existed in its most fundamental form, neither kinetic nor potential, but something more basic still. Scientists describe this using numbers that seem almost mystical. Temperatures of 10 to the power of 32 degrees Kelvin, energies of 10 to the power of 19 billion electron volts. These aren't just large numbers. They represent energy densities so extreme that they warp the very fabric of mathematical space-time. Yet within this apparent nothingness, something extraordinary was happening. Quantum fluctuations rippled through the vacuum. Not movements through space, for space didn't exist, but variations in the probability fields that would eventually give birth to reality itself. These fluctuations weren't random chaos, but followed patterns described by equations of breathtaking mathematical beauty. They were like gentle waves on a cosmic ocean that existed before the ocean, before waves, before the very concept of existence and non-existence. Think of these quantum fluctuations as the universe borrowing energy from its own future. In our everyday world, this borrowing happens constantly, but on scales so tiny and for durations so brief that we never notice. Virtual particles pop into existence, dance for infinitesimal moments, then annihilate back into the void, leaving no trace except subtle influences on the behavior of matter and energy around them. But in this primordial state, these borrowings were happening on a scale that encompassed all of reality. The mathematics describing this realm reads like poetry written in the language of infinity. Here, density approached infinite values, compressed into volumes approaching zero. Space-time curvature became so extreme that the distinction between matter and geometry dissolved. The equations that physicists use to describe this state, Einstein's field equations merged with quantum mechanics, produce results that seem to transcend logic itself, while remaining mathematically consistent and beautiful. In this perfect symmetry, there was no arrow of time pointing from past to future. Causality, that fundamental principle where causes precede effects, had no meaning because there was no sequence of events to unfold. Every moment contained every other moment. Every possibility existed simultaneously with every other possibility. It was a state of pure potential, like an unplayed symphony that contains within its silence every note that could ever be played. The energy that filled this pre-space wasn't distributed unevenly. There was no here or there for it to be distributed across. Instead, it existed in perfect homogeneity, each infinitesimal point identical to every other infinitesimal point. Yet, within this sameness, the seeds of difference were already present in the form of those quantum fluctuations, waiting for the moment when space and time would burst forth and give them room to grow into galaxies, stars, and worlds. Scientists sometimes describe this state using the concept of false vacuum. Not false in the sense of being untrue, but false in the sense of being unstable, like a ball balanced on the peak of a hill. In our analogy, the ball represents the unified field of energy and forces, perfectly balanced but inherently unstable. The slightest perturbation would send it rolling down into a new state, a state where the unified force would shatter into separate forces, where energy would condense into particles, where space and time would unfold like a flower, blooming and fast forward. But what could cause such a perturbation in a realm where there was no external influence, no outside force to provide a push? The answer lies in the quantum nature of reality itself. Even in perfect symmetry, quantum mechanics demands uncertainty. The Heisenberg uncertainty principle, which tells us that we cannot simultaneously know both the position and momentum of a particle with perfect precision, applies even to the vacuum itself. This uncertainty created spontaneous fluctuations that, in most cases, would simply cancel themselves out and disappear. However, in this specific configuration of energy and symmetry, one particular type of fluctuation had the potential to grow rather than disappear. Like a soap bubble forming in a perfectly still glass of water, this fluctuation would begin small but possess the remarkable property of being able to expand exponentially, carrying space and time along with it as it grew. The beauty of this primordial state lies not just in its mathematical elegance, but in its profound implications for understanding existence itself. It suggests that nothingness is not the opposite of something, but rather the pregnant void from which everything emerges. It tells us that the deepest reality is not solid matter or flowing energy, but the creative potential that underlies both. As we contemplate this realm before time itself, we begin to understand that the birth of our universe was not the beginning of everything, but rather the moment when everything that already existed in potential began to unfold into actuality. It was the instant when the perfect unified silence gave way to the complex, beautiful symphony of space, time, matter, and energy that we call reality. This primordial realm challenges our deepest assumptions about reality. We typically think of existence as binary, something either is or isn't. But this pre-space, pre-time state suggests that reality is more nuanced, more subtle. It existed in a state of pure being that transcended the need for physical manifestation. Like a master painter's blank canvas that already contains every possible masterpiece, this quantum vacuum held within it every star that would ever shine, every planet that would ever form, every moment of consciousness that would ever arise. The philosophical implications are as profound as the physical ones. If everything emerged from this state of unified potential, then at the deepest level, everything remains connected. The atoms in your body, the light from distant stars, the thoughts in your mind, all share this common origin in the quantum foam that preceded space and time. We are not separate observers looking at an external universe. We are the universe becoming aware of itself, temporary arrangements of the same fundamental energy that once existed in perfect unity. Scientists continue to probe deeper into understanding this primordial state, using particle accelerators to recreate tiny pockets of the extreme conditions that existed before the Big Bang. Each experiment brings us closer to understanding not just how the universe began, but why it began at all. The equation suggests that this transition from unified potential to diverse reality wasn't just possible, it was inevitable. The very nature of quantum uncertainty made it impossible for the perfect symmetry to persist forever. Yet, even as we develop increasingly sophisticated theories about this pre-beginning state, we must acknowledge the profound humility it demands of us. We are using minds that evolved to navigate a world of medium-sized objects moving at moderate speeds to contemplate conditions so extreme they existed before the concepts of size, speed, or even existence had meaning. It's like asking a fish to describe the experience of flight, or asking a musical note to explain the silence from which it emerged. From this state of infinite potential and perfect unity, something was about to emerge that would change everything forever. Not gradually, not slowly, but in a single moment so brief and so transformative that it would create not just the universe, but the very stage upon which the cosmic drama would unfold. The transition from this realm beyond space and time to the explosive birth of everything we know marks perhaps the most profound transformation in the history of existence itself. The Big Bang. How did everything come from nothing at all? From that perfect unified state we explored moments ago, where forces merged into one harmonious whole and energy existed in its purest form, something extraordinary was about to unfold. Not with violence or chaos, as the name Big Bang might suggest, but with a gentle, inevitable elegance that transformed pure potential into the rich tapestry of reality we inhabit today. The transition began not with an explosion in space, but as an expansion of space itself. Picture trying to imagine the surface of a balloon as it inflates, but instead of air filling the balloon, imagine that the rubber itself is what's expanding, carrying everything on its surface along for the ride. This analogy, while imperfect, helps us grasp how space-time itself began to stretch and unfold from that initial point of infinite density and temperature. In the first inconceivably small fraction of a second, a period so brief that light itself could barely travel the width of a proton, the universe underwent what scientists call cosmic inflation. During this phase, space expanded faster than the speed of light itself. This might seem to violate Einstein's cosmic speed limit, but remember, it wasn't matter or energy moving through space at this incredible rate. It was space itself that was expanding, carrying everything along with it like passengers on a cosmic escalator. The mathematics describing this moment are breathtaking in their precision. In just 10 to the power of -35 seconds, the universe expanded by a factor of at least 10 to the power of 26. To put this in perspective, if a single atom expanded at this rate, it would grow larger than a grapefruit in that same infinitesimal moment. The entire observable universe we see today, with its billions of galaxies spread across billions of light years, once fit comfortably in a region smaller than the period at the end of this sentence. But what drove this remarkable expansion? The answer lies in the nature of that false vacuum state we encountered in our previous exploration. Like water flowing downhill or a ball rolling from a mountaintop, the unified energy field began its transition to a lower, more stable state. As it did so, it released enormous amounts of energy, not the familiar energy of motion or heat, but something far more fundamental, the energy of space-time itself. This energy didn't dissipate into emptiness. Instead, it became the driving force behind inflation. Each cubic centimeter of expanding space contained the same energy density, which meant that as space grew, the total energy in the universe grew as well. This might seem to violate the conservation of energy, one of the most fundamental principles in physics, but in the curved space-time of the inflating universe, energy conservation takes on a more subtle meaning. During inflation, the universe remained remarkably smooth and uniform. The quantum fluctuations that existed in the pre-Big Bang state, those gentle ripples in the fabric of potential reality, were stretched along with space itself. Like tiny wrinkles in a balloon that become less noticeable as the balloon inflates, these fluctuations were smoothed out across vast distances. Yet, they weren't eliminated entirely. They were preserved as incredibly subtle variations in energy density that would later serve as the seeds for all the structure we see in the universe today. As inflation drew to a close, after perhaps 10 to the power of -32 seconds, the energy driving the expansion began to transform into something more familiar. The inflatant field, as physicists call it, started to decay, converting its energy into a hot, dense soup of fundamental particles and radiation. This moment, known as reheating, marked the transition from the exotic physics of inflation to the more familiar, though still extreme, conditions of the hot Big Bang. The temperature at this moment defied comprehension, roughly 10 to the power of 28 degrees Kelvin. At such temperatures, the distinction between matter and energy becomes meaningless. Particles pop into existence and annihilate back into pure energy in endless cycles. The four fundamental forces, which had been unified during inflation, began their gradual separation as the universe cooled and expanded. First to separate was gravity, that gentle but persistent force that would eventually shape the large-scale structure of the cosmos. As gravity decoupled from the other forces, space-time itself gained the ability to curve and bend in response to the energy and matter it contained. This was the moment when Einstein's general relativity began to govern the behavior of the expanding universe, providing the mathematical framework that still describes cosmic evolution today. The remaining three forces, electromagnetic, strong nuclear, and weak nuclear, continued their unified dance a bit longer. The energy density was still so extreme that particles we consider fundamental today, like protons and neutrons, couldn't yet form stable structures. Instead, the universe was filled with quarks and gluons, electrons and neutrinos, photons and exotic particles that exist only in the most extreme environments. As expansion continued, temperatures began to drop with mathematical precision. The relationship is beautifully simple. As the universe doubled in size, its temperature was cut in half. This cooling wasn't gradual by our standards. It happened incredibly rapidly. But it was smooth and predictable, following laws of physics that remain constant today. By the time the universe was about 10 to the power of -11 seconds old, still an unimaginably brief moment, the strong nuclear force separated from the electro-weak force. This transition released another burst of energy and created the conditions necessary for quarks to begin forming the first composite particles. The universe was beginning its long journey from perfect uniformity toward the rich complexity that would eventually include stars, planets, and life itself. During these earliest moments, the universe underwent several phase transitions, each one similar to water, freezing into ice or steam, condensing into liquid. But these weren't changes in ordinary matter. They were transformations in the fundamental fields that create and govern all particles and forces. Each transition released energy, created new particles, and established new patterns of behavior that would persist throughout cosmic history. The remarkable thing about this entire process is how smooth and predictable it was. Despite the extreme conditions and rapid changes, the universe evolved according to mathematical laws that we can understand and describe today. The same equations that govern a falling apple or the orbit of the moon also describe the expansion of space-time during those first crucial moments after the Big Bang. Throughout this period, the universe remained opaque to light. The temperature and density were so extreme that photons, particles of light, couldn't travel freely through space. Instead, they were constantly scattered by the dense soup of charged particles, like sunlight trying to penetrate a thick fog. The universe was brilliant with energy, but that brilliance was trapped, unable to shine across cosmic distances. This opacity would persist for hundreds of thousands of years, but already, in these first moments, the foundations were being laid for everything that would follow. The slight variations in density, stretched and preserved from the quantum fluctuations of the pre-Big Bang era, were establishing the patterns that would eventually become galaxy clusters, individual galaxies, and the vast cosmic web of matter and energy that structures our universe today. As we contemplate these first moments after the Big Bang, we encounter one of the most profound mysteries in all of science. How did something so complex and beautiful emerge from apparent nothingness? The answer seems to lie in the mathematical elegance of the physical laws themselves. These laws didn't emerge with the Big Bang. They seem to exist independently, providing the framework within which matter, energy, space, and time could unfold. Perhaps the most beautiful aspect of the Big Bang is that it reveals the universe to be fundamentally creative. Rather than a random explosion scattering debris across empty space, it was a carefully orchestrated unfolding of potential into actuality. Every star that would ever shine, every planet that would ever form, every moment of consciousness that would ever arise, all of it was implicit in the mathematical relationships that governed those first few moments of cosmic time. The Big Bang teaches us that creation isn't a single event, but an ongoing process. The same creative principles that brought forth space, time, matter, and energy from the quantum vacuum continue to operate today. Stars are still being born, planets are still forming, and the universe continues its expansion into an unknown future, carrying forward the creative impulses that began in that first miraculous moment when everything came from what appeared to be nothing at all. In those initial instants, the universe established the fundamental constants and relationships that would govern all subsequent evolution. The strength of gravity, the charge of an electron, the speed of light. All of these were determined by the conditions and processes of the Big Bang. It's as if the universe was composing the rules by which it would continue to create itself, writing the musical score for a cosmic symphony that continues to play today. From perfect unity to infinite diversity, from pure potential to manifest reality, the Big Bang represents the most dramatic transformation in the history of existence. Yet it unfolded with mathematical precision and elegant simplicity, demonstrating that, at the deepest level, the universe operates according to principles of harmony and order that transcend our everyday understanding of chaos and randomness. 1 second after. Why were the tiniest fractions of a second so incredibly important? As we continue our gentle journey through cosmic time, we arrive at a period that seems almost leisurely compared to the frantic pace of inflation, yet remains extraordinary by any measure we might apply. 1 full second after the Big Bang, a duration that feels instantaneous in our daily lives, represents an eternity in the early universe's rapid evolution. By this point, more transformative events had already occurred than would happen in the next several billion years combined. To understand why this single second was so monumentally important, we must first appreciate just how dramatically the universe had already changed. The temperature, which during inflation had reached heights beyond imagination, had now cooled to a comparatively modest 10 billion degrees Kelvin. While this remains far hotter than the core of any star, it marked a crucial threshold where the fundamental building blocks of matter could finally begin to organize themselves into stable forms. During this first second, the universe underwent what physicists call the era of nucleosynthesis, the first time in cosmic history when protons and neutrons could bind together to form atomic nuclei. This wasn't a gradual process, but a precisely timed cosmic ballet, choreographed by the fundamental forces and the expanding universe's cooling rhythm. The process began when the universe was just a few minutes old, but its stage was set during that crucial first second. At exactly the right temperature and density, the strong nuclear force could finally overcome the electromagnetic repulsion between positively charged protons. Like dancers waiting for the perfect musical cue, protons and neutrons began their intricate partnering that would create the first atomic nuclei in the universe. The most common dance was between a single proton and a single neutron, creating deuterium, heavy hydrogen. This might seem like a simple step, but it required exquisite timing. If the universe had been slightly denser, all the hydrogen would have been processed into heavier elements. If it had been slightly less dense, no complex nuclei would have formed at all. The conditions had to be precisely balanced within extremely narrow margins. Once deuterium formed, it quickly partnered with additional protons and neutrons to create helium-4 nuclei. This process was remarkably efficient, converting approximately 25% of the universe's protons into helium nuclei within just a few minutes. The remaining 75% remained as solitary protons, the nuclei of hydrogen atoms. This ratio of hydrogen to helium, determined in those first few minutes, would influence the evolution of stars and galaxies for billions of years to come. Tiny amounts of lithium-7 were also forged during this period, along with trace quantities of other light elements. But the nucleosynthesis process stopped there, limited by the rapidly cooling temperature and expanding space. Elements heavier than lithium would have to wait for the birth of the first stars, billions of years in the future, to make their debut in the cosmic story. The precision required for this nucleosynthesis to succeed reveals something profound about the universe's fundamental nature: the rates of expansion, the strengths of the nuclear forces, the masses of protons and neutrons. All of these had to fall within incredibly narrow ranges for complex nuclei to form at all. Change any of these parameters by even small amounts, and we would live in a universe composed entirely of hydrogen, or conversely, a universe with no hydrogen at all. During this same crucial period, another fundamental transformation was taking place. The 4 forces that govern all interactions in the universe had by now separated into their distinct identities, each taking on the characteristics we observe today. Gravity, though by far the weakest, had begun its patient work of gathering matter into slightly denser regions. These subtle variations in density amplified versions of those quantum fluctuations from before the Big Bang would eventually grow into the cosmic web of galaxies and galaxy clusters we see today. The electromagnetic force, now independent, governed the behavior of charged particles throughout the cosmos. Photons, particles of light, careened through the dense soup of matter and energy, but they couldn't travel far before colliding with electrons or other charged particles. The universe remained opaque, glowing with trapped light that couldn't escape to illuminate the cosmic distances. Meanwhile, the weak nuclear force continued its subtle but essential work, governing radioactive decay and certain types of particle interactions. Without this force, the balance between protons and neutrons established during the first second would have been different, dramatically altering the outcome of nucleosynthesis and the future evolution of the universe. The strong nuclear force, having recently separated from its unified state, now demonstrated its remarkable dual personality. At very short distances within atomic nuclei, it was overwhelmingly attractive, binding protons and neutrons together despite their electromagnetic repulsion. But at slightly larger distances, it effectively vanished, allowing atoms to maintain their distinct identities while permitting the chemical bonds that would eventually make complex molecules possible. As the universe continued to expand and cool during this first second, the energy density dropped to levels where exotic particles, those that exist only in extreme conditions, began to decay into more familiar forms. Strange quarks transformed into up and down quarks. Muons decayed into electrons. And the particle zoo that had populated the universe's earliest moments gradually simplified into the basic constituents we recognize today. This simplification wasn't random, but followed precise mathematical rules that determine which particles are stable under different conditions. Like a complex musical chord gradually resolving into a simple, harmonious note, the universe's particle content evolved toward the stable forms that would persist for billions of years. The neutrinos, those ghostly particles that barely interact with ordinary matter, also played a crucial role during this period. By the end of the first second, the universe had cooled enough that neutrinos could travel freely without constantly colliding with other particles. This moment, known as neutrino decoupling, created a cosmic neutrino background that still permeates the universe today, carrying information about conditions during that first crucial second. These relic neutrinos, now cooled to just a few degrees above absolute zero, vastly outnumber all the atoms in the universe. In every cubic centimeter of space around us, there are approximately 300 of these ancient messengers from the universe's first second. They pass through our bodies, through the Earth, through entire stars, as if these massive objects were made of the thinnest vapor. The temperature during this first second also determined another crucial aspect of the universe's future: the ratio of matter to antimatter. In the earliest moments, matter and antimatter existed in nearly equal quantities, constantly creating and annihilating each other in an endless dance of creation and destruction. But during the first second, a tiny asymmetry, perhaps just one extra matter particle for every billion matter-antimatter pairs, began to tip the cosmic balance. This slight preference for matter over antimatter, built into the fundamental laws of physics at levels we're still trying to understand, meant that when the universe cooled enough for the great annihilation to end, a small residue of matter remained. Every atom in every star, planet, and living being today exists because of this minuscule imbalance that manifested during the universe's first second. The mathematical elegance of these processes reveals something beautiful about the cosmos. The same physical laws that govern the behavior of atoms in a laboratory also governed the evolution of the entire universe during its most crucial moments. The quantum mechanics that describes the probability clouds of electrons around atomic nuclei also determined which particles would survive the transition from the exotic conditions of the early universe to the more familiar physics of today. By the end of this first second, the universe had established its fundamental character. The inventory of stable particles was complete, the ratio of different elements was determined, and the subtle density variations that would eventually become galaxies had been set in motion. The stage was prepared for the next act in the cosmic drama, the formation of the first atoms, and the beginning of the universe's long journey toward complexity. Yet even as we marvel at how much was accomplished in this brief span of time, we must remember that from the universe's perspective, this first second represented a gradual, almost leisurely cooling and expansion. The frantic energy of inflation had given way to a more measured evolution, governed by well-understood physical laws and proceeding with mathematical precision. The universe that emerged from this first second was simpler than what we see today, yet it contained within its structure and composition all the potential for the magnificent complexity that would unfold over the next 14 billion years. Every star that would ever shine, every planet that would ever form, every moment of consciousness that would ever arise, all of it was made possible by the precise conditions and transformations that occurred during those first precious moments after the Big Bang. Primordial Soup. How did matter survive the chaos of the universe's birth? In the gentle aftermath of that transformative first second, the universe entered what we might call its adolescent phase, no longer the explosive infant of its earliest moments, yet still far from the mature cosmos we inhabit today. The primordial soup that filled all of space during this era was unlike any substance we can directly experience, yet it contained within its swirling currents every atom that would eventually form stars, planets, and the intricate chemistry of life itself. Picture, if you will, a cosmic ocean stretching infinitely in all directions. Its waters composed not of hydrogen and oxygen molecules, but of the fundamental constituents of matter themselves. Protons and neutrons, electrons and photons, neutrinos, and the exotic remnants of earlier cosmic epochs all move through this medium in a complex dance governed by the interplay of temperature, density, and the fundamental forces of nature. The temperature of this primordial soup was still extraordinary by earthly standards, roughly 1 billion degrees Kelvin, yet it represented a dramatic cooling from the conditions we explored in previous moments. At this temperature, atomic nuclei could maintain their integrity, but the electromagnetic environment remained far too energetic for complete atoms to form. Electrons, those essential partners in atomic structure, move freely through space, unbound to any particular nucleus. This state of matter, known as a plasma, created conditions of remarkable uniformity throughout the universe. Unlike the complex structures we see today, galaxies separated by vast voids, stars concentrated in spiral arms, planets orbiting in organized systems, the primordial soup was almost perfectly smooth. The density varied by less than 1 part in 100,000 from one region to another, a homogeneity so extreme that if Earth's surface were this uniform, the highest mountains would rise only a few centimeters above the deepest ocean trenches. Yet, within this apparent sameness lay the seeds of all future complexity. Those tiny density variations, stretched and amplified from quantum fluctuations that existed before space and time themselves, were already beginning their slow but inevitable evolution toward structure. In regions where the density was even slightly higher than average, gravity began its patient work of gathering additional matter, while slightly less dense regions gradually became more empty as their contents migrated toward the denser areas. The survival of matter during this era was far from guaranteed. The universe remained filled with high-energy photons, particles of light, that carried enough energy to break apart atomic nuclei if they encountered them at just the right angle. It was a delicate balance. Temperatures had to be low enough for nuclei to remain stable, yet the universe was still hot enough that these destructive photons were constantly being created and absorbed throughout the cosmic medium. The electromagnetic force played a crucial role in maintaining this balance. As the universe expanded and cooled, the energy of individual photons decreased according to precise mathematical relationships. The wavelength of light stretched along with space itself, gradually shifting from the high-energy gamma rays that could destroy nuclei toward the lower-energy forms that would eventually become visible light, then infrared radiation, and finally the microwave background radiation we can detect today. During this period, the universe experienced what physicists call thermal equilibrium, a state where energy was constantly being exchanged between different forms, but the overall distribution remained stable and predictable. Photons collided with electrons, electrons interacted with nuclei, and particles were constantly being created and destroyed in a complex web of interactions that maintain the soup's fundamental character while allowing it to evolve slowly as expansion and cooling continued. The chemistry of this primordial era was remarkably simple compared to what would come later. The nuclear processes that had operated during the first few minutes had produced primarily hydrogen and helium nuclei, with trace amounts of lithium and other light elements. The hydrogen nuclei, simple protons, made up about 75% of all atomic nuclei, while helium-4 nuclei comprised nearly all of the remaining 25%. This elemental composition, determined by the precise conditions during nucleosynthesis, would remain essentially unchanged for hundreds of millions of years. What made this soup truly primordial was not just its composition, but its relationship to the fundamental forces that govern all matter. The strong nuclear force, which binds protons and neutrons together within atomic nuclei, operated at its full strength, ensuring that the nuclei formed during the first few minutes remained stable despite the energetic environment. The electromagnetic force governed the behavior of charged particles, protons and electrons, creating the complex interactions that would eventually lead to the formation of neutral atoms. The weak nuclear force, though less obvious in its effects, continued to play subtle but important roles in maintaining the balance between different types of particles. Occasionally, a proton would transform into a neutron, or vice versa, through weak force interactions, but these changes were rare enough that the overall composition of the soup remained stable. Gravity, the weakest of the four fundamental forces, was nevertheless beginning to assert its influence on the largest scales. While individual particles felt almost no gravitational attraction to their neighbors, the collective gravitational effect of vast regions of space was slowly but inexorably drawing matter toward the areas of slightly higher density. This process operated so gradually that it would take hundreds of millions of years to produce noticeable results. Yet, it had already begun during this primordial epoch. The photons that filled this cosmic soup weren't simply passive participants, but active agents in maintaining its character. These particles of light carried most of the universe's energy, and their interactions with matter determined many of the soup's properties. When a photon collided with an electron, it could scatter in a new direction, carrying energy and momentum to different parts of the universe. This constant scattering meant that light couldn't travel far without being redirected, making the universe opaque despite being filled with brilliant radiance. The mathematical description of this primordial soup reveals its deep connection to fundamental physics. The relationship between temperature, density, and pressure followed the same equations that govern the behavior of gases and plasmas today. The rate of cooling was determined by the expansion of space itself, which in turn was governed by Einstein's equations of general relativity. The interactions between particles followed the rules of quantum mechanics, creating probability distributions that determined which collisions would occur and what their outcomes would be. As time passed, and we're speaking of periods measured in tens of thousands of years, the gradual cooling of the universe began to approach a crucial threshold. The temperature was slowly dropping toward the point where electrons would have low enough energies to be captured by atomic nuclei, forming the first complete atoms in cosmic history. But this transition was still far in the future, allowing the primordial soup to maintain its plasma state for much longer periods. During this extended era, the universe's expansion continued at a rate determined by the total energy density of space itself. Unlike the exponential inflation of the earliest moments, this expansion followed a more leisurely mathematical relationship. As time doubled, the size of the universe increased by a factor of the square root of 2. This more gradual expansion allowed the various components of the primordial soup to remain in thermal equilibrium, sharing energy efficiently through countless particle interactions. The neutrinos that had decoupled during the first second continued their journey through this cosmic medium, but they were now essentially invisible to the other components of the soup. These ghostly particles, created in vast numbers during the universe's first moments, traveled through the plasma without interacting, carrying information about those earliest conditions toward a future when sensitive detectors might someday capture their ancient message. The beauty of this primordial era lies in its essential simplicity combined with its profound potential. The soup was governed by well-understood physical laws, operating under extreme but stable conditions. Every particle interaction, every energy exchange, every subtle gravitational influence followed patterns that we can describe mathematically and predict with precision. Yet, within this ordered simplicity, the conditions were being established for all the complexity that would follow. The density fluctuations that would eventually become galaxies were growing imperceptibly larger. The elemental composition that would determine the properties of the first stars was locked in place. The thermal history that would govern the universe's cooling was following its predetermined path. In essence, the primordial soup contained within its uniform expands the blueprint for every structure that would emerge over the next 14 billion years. Perhaps most remarkably, this cosmic soup survived its own chaotic birth not through luck or accident, but through the elegant interplay of fundamental forces and mathematical relationships. The same physics that allows atoms to remain stable in our bodies today also ensured that atomic nuclei could survive the extreme conditions of the early universe. The same forces that govern chemical reactions in our laboratories also maintain the balance between creation and destruction in the primordial plasma. As we contemplate this ancient era, we begin to understand that the universe's evolution from simplicity to complexity wasn't a random process, but a carefully orchestrated unfolding of potential into actuality. The primordial soup represents a crucial stage in this evolution. The calm after creation's initial storm, yet pregnant with all the possibilities that would eventually fill the cosmos with stars, galaxies, and the countless wonders we observe today. The survival of matter through this primordial epoch demonstrates the universe's fundamental stability and resilience. Despite the extreme conditions and constant activity, the essential building blocks of reality persisted, evolved, and prepared for the next great transformation that awaited them in the cosmic future. Cosmic Dark Ages. Why did the universe go completely dark for millions of years? As our cosmic journey continues through the gentle flow of deep time, we arrive at one of the most profound and peaceful periods in the universe's history. An era so fundamentally different from our modern cosmos that it challenges our very conception of what it means for the universe to exist. The cosmic dark ages weren't dark because of an absence of energy or activity, but rather because light itself had become imprisoned within the very fabric of space, unable to travel the vast distances that would allow it to illuminate the cosmic depths. This transformation began approximately 380,000 years after the Big Bang, when the universe had cooled to a temperature of about 3,000 degrees Kelvin, still far hotter than the surface of most planets, but cool enough for one of the most significant transitions in cosmic history to unfold. For the first time since the earliest moments after creation, electrons and atomic nuclei could unite in stable partnership, forming complete atoms that would persist for millions of years. The process, known as recombination, unfolded with mathematical precision across the entire universe simultaneously. As temperatures dropped below the critical threshold, electrons, which had been racing freely through the cosmic plasma for hundreds of thousands of years, began to slow down enough that they could be captured by the electromagnetic attraction of atomic nuclei. Hydrogen nuclei, simple protons that had been created during the first few minutes after the Big Bang, became the universe's first complete atoms, as they each captured a single electron to achieve electrical neutrality. This cosmic transformation was remarkably swift by astronomical standards, taking only a few thousand years to sweep through the entire observable universe. The effect was dramatic and immediate. Photons, which had been constantly scattered by free electrons in the primordial plasma, suddenly found themselves in a universe composed primarily of electrically neutral atoms. Without charged particles to interact with, these photons could finally travel freely through space, carrying their ancient light toward destinations unimaginably distant. But here lies the beautiful paradox of the cosmic dark ages. At the moment when light was finally liberated to travel freely through the universe, that same universe entered its darkest period. The photons that had been trapped since the earliest moments began their journey carrying the thermal glow of recombination, a warm, reddish light that filled all of space. However, as these photons traveled through the expanding universe, their wavelengths stretched along with space itself, gradually shifting from visible light into infrared radiation, then into microwaves, and finally into the faint background radiation we can detect today. Within a few million years, this ancient light had stretched beyond the range of what we would recognize as illumination, leaving the universe in a state of profound darkness that would persist for hundreds of millions of years. No stars yet existed to break this cosmic night. No galaxies shone in the void. No supernovae painted brief masterpieces across the sky. The universe had entered a period of patient waiting, its matter slowly organizing itself under the gentle guidance of gravity's invisible hand. Yet this darkness was far from empty or inactive. Throughout the cosmic dark ages, the universe teemed with invisible activity as the structures we see today began their slow formation. The tiny density variations that had been preserved from the quantum fluctuations of the pre-Big Bang era and which had grown slowly during the Primordial Soup phase now began to evolve more rapidly in the absence of the radiation pressure that had previously resisted their gravitational collapse. Dark matter, that mysterious substance that outweighs ordinary matter by a factor of 5 to 1, played the leading role in this cosmic choreography. Unaffected by the electromagnetic interactions that had kept ordinary matter coupled to photons, dark matter had begun forming gravitational wells even before recombination occurred. These invisible scaffolds provided the framework around which ordinary matter would eventually organize itself into the first stars and galaxies. The mathematics describing this period reveals a universe of exquisite subtlety and patience. Gravitational attraction worked slowly but inexorably, drawing matter from regions of slightly lower density toward regions of slightly higher density. The process followed precise power laws and scaling relationships that astronomers can calculate and verify through computer simulations. What began as variations of 1 part in 100,000 gradually grew into density contrasts of 2 to 1, then 10 to 1, then 100 to 1. During these dark ages, the universe's composition remained remarkably stable. Approximately 73% of the cosmos consisted of hydrogen atoms, 25% helium atoms, and tiny traces of lithium, the same elemental ratios that had been established during nucleosynthesis in the first few minutes after the Big Bang. No heavier elements existed anywhere in the universe. Carbon, oxygen, silicon, iron, all the elements that would eventually make rocky planets and complex chemistry possible, awaited the birth of the first stars for their creation. The temperature throughout this period continued to drop, according to the mathematical relationship established by cosmic expansion. As the universe doubled in size, its temperature halved, creating a slow but steady cooling that would eventually bring the cosmic background temperature down to the few degrees above absolute zero that we measure today. This cooling wasn't uniform, however. Regions of higher density remained slightly warmer than average, while less dense regions cooled slightly faster, creating temperature variations that mirrored the developing structure in the distribution of matter. The physics governing the Dark Ages was dominated by gravity and the statistical mechanics of gas dynamics. Without the complex nuclear processes that power stars, or the electromagnetic phenomena that create the aurora and lightning we know on Earth, the universe's behavior could be described by relatively simple equations. Yet from this simplicity emerged the seeds of all future complexity. As gravitational instabilities grew and matter began to flow along preferred directions determined by the underlying web of dark matter. Computer simulations of this period reveal a universe that resembled a vast three-dimensional spider web, with filaments of dark matter stretching across millions of light years, connected at intersection points where the density was highest. Ordinary matter, following the gravitational guidance of this invisible framework, began to flow along these filaments like water following the courses of ancient riverbeds. At the nodes where multiple filaments intersected, matter accumulated in ever-growing concentrations that would eventually become the birthplaces of the first galaxies. The scale of structures during the Dark Ages was enormous compared to anything we see in the universe today. The first gravitationally bound objects to form were not individual stars or even galaxies, but vast collections of matter with masses millions of times greater than our Sun, spread across regions hundreds of light years in diameter. These primordial structures, composed entirely of hydrogen and helium gas embedded within invisible dark matter halos, represented the universe's first attempt at creating organized complexity from the smooth simplicity of the post-recombination era. Throughout this period, the cosmic neutrino background, those ghostly particles that had decoupled during the first second after the Big Bang, continued their unimpeded journey through space, by now cooled to just a few degrees above absolute zero. These relic neutrinos carried information about the universe's earliest moments through the darkness, invisible messengers from a time when the cosmos was unimaginably different from its dark age configuration. The end of the cosmic dark ages was not predetermined by any cosmic clock, but rather emerged naturally from the gravitational processes that had been operating throughout this period. As matter continued to accumulate in the densest regions of the cosmic web, some of these accumulations eventually reached critical thresholds, where the gravitational compression became intense enough to trigger nuclear fusion. The universe was preparing for one of the most dramatic transitions in its history, the ignition of the first stars. Yet, even as we anticipate this cosmic dawn, we must appreciate the essential role that the Dark Ages played in preparing the stage for all subsequent cosmic evolution. During this long period of apparent inactivity, gravity performed the crucial work of organizing matter into the hierarchical structures that would eventually become galaxies, galaxy clusters, and the vast cosmic web we observe today. The Dark Ages demonstrate that cosmic evolution operates on time scales that dwarf human experience, yet follows mathematical principles we can understand and verify. The same gravitational physics that causes an apple to fall to Earth also guided the formation of structures spanning millions of light years during this ancient epoch. The same statistical mechanics that describes the behavior of gases in a laboratory also governed the movement of matter through the expanding universe during its darkest period. Perhaps most remarkably, the cosmic Dark Ages reveal that darkness and light are not opposites in the cosmic context, but rather different phases in an ongoing cycle of creation and illumination. The darkness was not an absence, but a presence, a time when the universe gathered its resources and organized its matter in preparation for the spectacular light show that would follow. It was a period of cosmic meditation, when the universe contemplated the structures it would soon bring forth from the patient work of gravity and time. As we reflect on this remarkable epoch, we begin to understand that the Dark Ages were not a pause in cosmic evolution, but an essential chapter in the ongoing story of creation. The darkness was pregnant with possibility, filled with invisible activity that would soon burst forth in the brilliant light of the first stars, ending the cosmic night and beginning a new era of luminous complexity that continues to this day. First light. How did the very first stars ignite and light up the void? After hundreds of millions of years of cosmic darkness, the universe was about to experience one of the most beautiful and transformative moments in its entire history. The patient work of gravity, operating invisibly throughout the Dark Ages, had finally gathered enough matter in certain privileged locations to cross a threshold that would change everything. The first stars were about to ignite, bringing light to a cosmos that had known only darkness since the ancient glow of recombination faded into the stretched wavelengths of cosmic expansion. These primordial stars were unlike anything we see in our modern universe. Born from clouds of pure hydrogen and helium, the only elements that existed at the time, they were giants in every sense, with masses typically 100 to 300 times greater than our Sun. Their formation began in the deepest gravitational wells created by dark matter, where ordinary matter had been accumulating for millions of years, slowly growing denser and more concentrated under the gentle but persistent pull of gravity. The process of star formation during this epoch unfolded with a majesty that defies easy description. Picture vast clouds of primordial gas, each containing enough matter to create thousands of sun-like stars, slowly contracting under their own gravitational attraction. As these clouds shrank, they began to spin faster, much like a figure skater pulling in her arms during a pirouette. The conservation of angular momentum, the same principle that governs spinning ice dancers and rotating galaxies, caused these primordial gas clouds to flatten into rotating disks while continuing their relentless gravitational collapse. At the centers of these spinning disks, matter accumulated with increasing density and temperature. Unlike the star formation we observe today, which is aided by the cooling effects of heavy elements and dust, these primordial clouds had only the most basic atomic physics to regulate their collapse. Hydrogen atoms collided with increasing frequency as the density rose, occasionally forming hydrogen molecules, the simplest possible molecular bonds in nature. These fragile molecules provided the only available mechanism for the gas to radiate away excess energy and continue its collapse toward the critical conditions needed for nuclear fusion. The mathematics governing this process reveal the elegant simplicity underlying cosmic complexity. As gravitational potential energy converted to kinetic energy through the cloud's collapse, temperatures at the center began to rise, according to well-understood thermodynamic relationships. When the core temperature reached approximately 10 million degrees Kelvin, a threshold determined by the quantum mechanical properties of hydrogen nuclei, something magical happened. Protons began to overcome their mutual electromagnetic repulsion and fuse together, releasing enormous amounts of energy in the process. The moment of first ignition must have been extraordinary. After hundreds of millions of years of darkness, a single point of light suddenly blazed forth in the cosmic void. The nuclear fusion reactions at the star's core generated temperatures of tens of millions of degrees, creating a brilliant beacon that could outshine entire modern galaxies. The energy released by converting hydrogen into helium through nuclear fusion created radiation pressure that balanced the inward pull of gravity, establishing the stable equilibrium that defines a star's main sequence lifetime. But these first stars were not destined for the billions of years of steady burning that characterize smaller stars like our Sun. Their enormous mass meant that nuclear fusion proceeded at a furious pace, consuming their hydrogen fuel in just a few million years. A brief moment by cosmic standards, yet long enough to fundamentally transform the universe around them. The light from these primordial stars didn't simply illuminate their immediate surroundings. It began the process of cosmic reionization, one of the most important phase transitions in the universe's history. The high-energy ultraviolet photons streaming from these stellar furnaces possessed enough energy to strip electrons away from hydrogen atoms, recreating the ionized plasma conditions that had existed before recombination, but now in localized bubbles around each star. As more and more first-generation stars ignited across the universe, these bubbles of ionized gas began to grow and merge, gradually filling the space between galaxies with a thin plasma of free electrons and protons. This process, which took several 100 million years to complete, marked the end of the cosmic dark ages and the beginning of the universe's current transparent phase, where light can travel freely across cosmic distances. The nuclear processes operating within these primordial stars were fundamentally different from those in modern stars. With only hydrogen and helium available as fuel, the fusion reactions followed relatively simple pathways. Hydrogen nuclei, protons, combined through a series of steps to create helium nuclei, releasing energy, neutrinos, and positrons in the process. The absence of heavier elements meant that these stars burned hotter and brighter than their modern counterparts, creating the extreme luminosities needed to ionize the surrounding universe. As these massive stars evolved, their cores became hot enough to fuse helium into carbon, then carbon into oxygen, then oxygen into silicon, and finally silicon into iron. For the first time in cosmic history, elements heavier than lithium were being created. Each fusion process required higher temperatures and pressures, causing the star's core to contract and heat up in a series of carefully orchestrated phases. The mathematical beauty of stellar nucleosynthesis lies in its precision. Each element is forged under specific conditions that depend on fundamental constants of physics, like the strong nuclear force and electromagnetic interactions. The creation of heavy elements within these stellar cores followed patterns that would determine the chemical evolution of the universe for billions of years to come. Carbon, the foundation of organic chemistry, formed when 3 helium nuclei combined in a process so precise that a slight change in nuclear physics would have prevented its formation entirely. Oxygen, essential for water and most biological processes, emerged from the fusion of carbon and helium nuclei. Silicon, iron, and dozens of other elements were forged in the extreme temperatures and pressures of these stellar furnaces. But perhaps the most important contribution of the first stars came at the end of their brief lives. With cores composed of iron, an element that cannot release energy through further fusion, these massive stars faced a crisis. The nuclear fires that had supported them against gravitational collapse could no longer provide the necessary energy, and gravity finally won the ancient battle. The stellar cores collapsed in milliseconds, creating conditions so extreme that protons and electrons were crushed together to form neutrons, releasing enormous amounts of energy in the process. The result was the universe's first supernova, explosions so powerful they could outshine entire galaxies for months. These cosmic detonations served multiple crucial functions in the universe's evolution. First, they dispersed the heavy elements created in stellar cores throughout the surrounding space, enriching the primordial hydrogen and helium with the carbon, oxygen, silicon, and iron that would eventually make rocky planets and complex chemistry possible. Second, the shock waves from these explosions compressed nearby gas clouds, triggering the formation of new generations of stars. Unlike their massive predecessors, these second-generation stars formed from gas clouds that now contain small amounts of heavy elements, enough to provide more efficient cooling mechanisms and allow the formation of smaller, longer-lived stars more similar to our Sun. The energy released by the first supernovae also contributed to cosmic reionization, adding to the ionizing radiation produced by the stars themselves. The combined effects of stellar radiation and supernova shock waves created a universe that was becoming increasingly transparent to light, setting the stage for the formation of the first galaxies and the complex structures we observe today. The location of these first stars was not random, but followed the invisible architecture established by dark matter during the cosmic dark ages. They ignited preferentially at the intersections of the cosmic web, where dark matter filaments crossed and created the deepest gravitational wells. This pattern of star formation helped establish the hierarchical structure of cosmic evolution, where small objects formed first and then assembled into larger and more complex systems over time. The spectroscopic signatures of these first stars would have been dramatically different from anything we observe in the modern universe. With no heavy elements in their atmospheres, their light would have shown only the absorption lines of hydrogen and helium, creating spectra of pristine simplicity. The absence of metals, as astronomers call all elements heavier than helium, meant that these stars could achieve temperatures and luminosities impossible for metal-rich stars in the current epoch. As we contemplate the ignition of the first stars, we witness a cosmic coming of age, the moment when the universe began to illuminate itself from within, creating light through its own processes rather than simply preserving the fading glow from its birth. These stellar pioneers were both creators and destroyers, forging the heavy elements essential for complexity, while burning through their fuel so rapidly that each one lasted only a few million years. The legacy of the first stars extends far beyond their brief lifetimes. Every atom of carbon in our bodies, every molecule of oxygen we breathe, every grain of silicon in Earth's rocks. All of these elements were first created in the nuclear furnaces of primordial stars that lived and died before our galaxy had fully formed. We are, quite literally, made of star stuff, connected across billions of years to those first bright beacons that ended the cosmic dark ages and began the universe's long journey toward the rich complexity we see today. The first light was not just illumination, but creation itself. The moment when the universe began to actively forge the ingredients for planets, life, and consciousness, transforming the simple perfection of hydrogen and helium into the magnificent diversity of elements that would eventually give rise to everything we know and cherish. The birth of galaxies. What invisible forces shaped the cosmic web? As the first stars began to fade and explode across the cosmic landscape, their brilliant light revealed something extraordinary that had been growing invisibly throughout the dark ages. The universe was not a uniform expanse dotted with isolated points of light, but rather an intricate tapestry of structure, a vast cosmic web of matter and energy that stretched across billions of light years, connecting every region of space in an elegant network of filaments, nodes, and voids. The birth of galaxies was not a sudden event, but a gradual awakening, as if the universe itself were slowly becoming conscious of its own architecture. The invisible scaffolding of dark matter, which had been patiently organizing itself according to gravitational mathematics for hundreds of millions of years, finally became visible as ordinary matter began to flow along its predetermined pathways, lighting up like electric current following the wires in a cosmic circuit board. This cosmic web represents one of the most beautiful examples of emergence in nature, the spontaneous appearance of complex, organized structure from simple underlying rules. The only forces at work were gravity and the expansion of space itself. Yet from these basic ingredients arose a hierarchical architecture of breathtaking elegance, thin filaments of dark matter, each containing the mass of millions of stars stretched across the void to connect dense nodes where galaxies would eventually form. Between these filaments lay vast empty regions, cosmic voids that contained almost no matter at all. The mathematical description of this process reveals deep connections between the quantum mechanical fluctuations that existed before the Big Bang and the large-scale structure we observe today. Those tiny variations in density, preserved and stretched during cosmic inflation, evolved according to precise statistical relationships that astronomers can calculate and verify through computer simulations. The same Gaussian random fields that describe quantum vacuum fluctuations also describe the distribution of galaxies across cosmic scales, a profound connection between the microscopic and macroscopic realms. Galaxy formation began at the intersections of this cosmic web, where multiple dark matter filaments converged to create the deepest gravitational wells in the universe. These locations, determined by the primordial density fluctuations, became assembly points where matter from vast surrounding regions slowly accumulated over hundreds of millions of years. The process was hierarchical, with smaller structures forming first and then merging to create larger and more complex systems. The first proto-galaxies were quite different from the majestic spiral and elliptical galaxies we see today. They were smaller, more irregular, and dominated by the intense star formation, triggered by their ongoing assembly. As gas clouds collided and merged within these gravitational wells, the resulting compression and turbulence created ideal conditions for rapid stellar birth. These early galaxies blazed with the light of young, massive stars, their spectra dominated by the blue and ultraviolet radiation, characteristic of stellar nurseries. Dark matter played the starring role in this cosmic choreography, even though it remained completely invisible to direct observation. Making up approximately 27% of the universe's total mass energy, dark matter interacted gravitationally with ordinary matter, but was immune to electromagnetic forces. This meant that while ordinary matter could be heated, ionized, and dispersed by stellar radiation and supernova explosions, dark matter remained unaffected, providing a stable gravitational framework that persisted through even the most violent phases of galaxy assembly. The nature of dark matter itself remains one of the most profound mysteries in modern physics, yet its effects on galaxy formation are crystal clear. Computer simulations show that without dark matter's gravitational influence, ordinary matter would never have been able to organize itself into the complex structures we observe. The universe would have remained a nearly uniform distribution of gas, with only the faintest density variations inherited from the primordial fluctuations. As proto-galaxies continued to grow through mergers and accretion, they began to develop the distinct morphologies we recognize today. The interplay between gravitational dynamics, gas physics, and stellar feedback created a rich variety of galactic forms. Some systems developed rotating disks, where gas settled into stable circular orbits and formed the spiral arm patterns that characterize galaxies like our Milky Way. Others experienced more violent merger histories that disrupted ordered rotation and created the smooth, elliptical profiles of giant elliptical galaxies. The formation of galactic disks represents one of the most elegant examples of physical principles operating on cosmic scales. As gas fell into the gravitational wells created by dark matter halos, It carried with it angular momentum, the rotational energy inherited from the initial turbulent motions of the early universe. Conservation of angular momentum, the same principle that governs spinning figure skaters and planetary orbits, caused this infalling gas to settle into thin, rotating disks where star formation could proceed in an organized fashion. The spiral arm patterns that developed in these disk galaxies emerged from a beautiful interplay between gravitational dynamics and stellar physics. Density waves propagating through the galactic disk compressed gas clouds as they passed, triggering episodes of star formation that illuminated the spiral structure. These waves were not material structures, but rather patterns of compression and rarefaction, similar to sound waves in air that move through the disk at speeds different from the orbital velocities of individual stars and gas clouds. Meanwhile, the massive elliptical galaxies formed through a different pathway, violent mergers between smaller proto-galactic systems. When two or more galaxies collided and merged, the resulting gravitational chaos disrupted any ordered rotation that might have existed, scrambling stellar orbits and creating the smooth, spheroidal distributions characteristic of elliptical systems. These merger events were among the most energetic processes in the universe, capable of triggering massive bursts of star formation and feeding the supermassive black holes that lurk at galactic centers. The cosmic web itself played a crucial role in determining which galaxies would form, where and what types they would become. Galaxies forming at the intersections of multiple filaments, where matter accumulated most rapidly, tended to become massive ellipticals through frequent mergers. Systems forming along individual filaments, with more sedate accretion histories, were more likely to develop into spiral galaxies with organized disk structures. The feedback processes connecting star formation, stellar death, and galaxy evolution created complex cycles that regulated the growth and development of galactic systems. Massive stars, burning through their nuclear fuel in just a few million years, ended their lives in spectacular supernova explosions that enriched the surrounding gas with heavy elements while simultaneously heating and dispersing material that might otherwise have formed additional stars. This stellar feedback created a delicate balance between star formation and stellar destruction that helped determine the final properties of mature galaxies. The supermassive black holes that formed at the centers of most galaxies added another layer of complexity to this cosmic ballet. As matter fell into these gravitational monsters, it released enormous amounts of energy that could heat surrounding gas to temperatures of millions of degrees, creating powerful outflows that affected star formation throughout the host galaxy. The relationship between central black holes and their host galaxies appears to be remarkably tight, suggesting that these seemingly disparate components co-evolved through processes we are still working to understand. The element enrichment history of galaxies reveals another fascinating aspect of their birth and evolution. The first generation of stars, composed entirely of hydrogen and helium, began the process of cosmic chemical evolution by creating and dispersing heavier elements through supernova explosions. Each subsequent generation of stars formed from gas that was slightly more enriched with these heavy elements, allowing for more efficient cooling, smaller stellar masses, and longer stellar lifetimes. This chemical evolution proceeded at different rates in different types of galaxies, creating a diversity of stellar populations that we can observe today. Massive elliptical galaxies, with their violent early histories and rapid star formation, quickly processed their gas into stars and achieved high levels of chemical enrichment. Spiral galaxies, with their more gradual and sustained star formation histories, show ongoing chemical evolution that continues to the present day. The cosmic web itself evolved as galaxies formed and matured within its structure. The gravitational influence of growing galactic systems helped to sharpen the contrast between high-density filaments and low-density voids. Gas was gradually processed from the diffuse intergalactic medium into the dense environments of galaxy-forming regions, leaving behind vast cosmic voids that became increasingly empty as cosmic time progressed. Perhaps most remarkably, the entire process of galaxy formation and cosmic web evolution can be understood through the application of fundamental physical principles operating over vast scales of space and time. The same gravitational physics that governs planetary orbits also shaped the cosmic web, The same thermodynamics that describes gas behavior in laboratories also governed the cooling and heating of primordial gas clouds. The same nuclear physics that powers the sun also enriched the universe with the heavy elements essential for planetary formation and biological chemistry. As we contemplate the birth of galaxies, we witness the universe's transition from simplicity to complexity, from smooth uniformity to rich structural diversity. The cosmic web represents the universe's first great architectural achievement, a framework of matter and energy that would provide the foundation for all subsequent cosmic evolution, including the formation of solar systems, planets, and ultimately the emergence of life itself. The invisible forces that shape this cosmic web, gravity, dark matter, and the expansion of space, continue to operate today, gradually assembling ever larger structures as galaxy clusters merge and the cosmic web becomes increasingly pronounced over cosmic time. We are living within this ongoing architectural project, temporary residents of a universe that continues to build itself according to mathematical principles of stunning elegance and precision. Elemental origins. How are the atoms in your body connected to ancient stars? Within your body at this very moment lies a profound connection to the deepest history of the cosmos. Every breath you take, every beat of your heart, every thought that passes through your mind depends on atoms that were forged billions of years ago in the nuclear furnaces of dying stars. The carbon in your muscles, the oxygen in your blood, the calcium in your bones, all of these elements carry within them the memory of stellar explosions that occurred long before our planet even existed. This remarkable truth represents one of the most beautiful discoveries in modern astronomy. We are not separate from the universe, but intimately woven into its very fabric. The elements that make life possible were created through cosmic processes of extraordinary violence and beauty, then scattered across space to eventually find their way into the molecular machinery that powers every living thing on Earth. The story begins with the universe's earliest moments, when only the three lightest elements existed anywhere in the cosmos. Hydrogen, helium, and trace amounts of lithium were the sole products of the Big Bang's nuclear furnace, created during the first few minutes when temperatures throughout space were hot enough to sustain nuclear fusion reactions. For hundreds of millions of years, these three elements represented the complete chemical inventory of the universe, a remarkably simple composition that would need to be dramatically enriched before planets and life could become possible. The transformation began when the first generation of massive stars ignited across the cosmic landscape. These stellar giants, containing hundreds of times more mass than our sun, burned through their nuclear fuel at a furious pace, reaching core temperatures of hundreds of millions of degrees. At these extreme temperatures, hydrogen nuclei fused into helium, then helium into carbon, carbon into oxygen, oxygen into silicon, and silicon into iron, following a precise sequence determined by the fundamental properties of atomic nuclei. Carbon, the foundation of all organic chemistry, formed through one of the most remarkable coincidences in physics. For carbon to be created in stellar cores, three helium nuclei must combine almost simultaneously, a process that seems highly improbable until we consider that stellar cores contain trillions upon trillions of helium nuclei, colliding billions of times per second. The specific nuclear properties that make this triple alpha process possible were so finely tuned that even a slight change in the fundamental forces would have prevented carbon formation entirely. Oxygen emerged from the fusion of carbon and helium nuclei, a process that required even higher temperatures and pressures than the carbon formation. This element, essential for water and most biological processes, could only be created in the hottest stellar cores, where gravitational compression generated conditions more extreme than anything we can produce on Earth. The nuclear reactions that created oxygen also produced neon, magnesium, and silicon, elements that would eventually become essential components of rocky planets. As these massive stars continued their nuclear evolution, their cores became layered like onions, with different fusion processes operating at different depths. The outermost layers continued burning hydrogen into helium, while deeper regions fused helium into carbon and oxygen. At the very center, where temperatures reached billions of degrees, silicon nuclei combined to form iron, the most stable nucleus in nature, and the endpoint of energy-releasing fusion reactions. Iron's special stability created a crisis for these stellar giants. Unlike lighter elements, iron cannot release energy through further fusion, which means that once a star's core becomes dominated by iron, the nuclear fires that have supported it against gravitational collapse can no longer provide the necessary energy. With nuclear fusion no longer able to support the star against its own gravity, the iron core collapsed in a matter of milliseconds, shrinking from a sphere larger than Earth to a ball just 20 kilometers across. This collapse released more energy than the star had produced during its entire previous lifetime, creating a shockwave that raced outward through the stellar layers at speeds of 30,000 kilometers per second. This supernova explosion became the crucible where elements heavier than iron were finally created. The intense neutron flux generated during core collapse allowed rapid neutron capture processes to build nuclei far more massive than iron, creating elements like copper, zinc, silver, gold, and uranium. But perhaps even more important than creating heavy elements was the supernova's role in dispersing them throughout space. The explosion's tremendous energy drove stellar material outward at thousands of kilometers per second, creating expanding shells of enriched gas that mixed with the primordial hydrogen and helium of the interstellar medium. For the first time in cosmic history, space between the stars became populated with the chemical diversity necessary for complex chemistry and planetary formation. The shock waves from these explosions also triggered the formation of new generations of stars from nearby gas clouds. Unlike their massive predecessors, these second-generation stars formed from material that now contains small but crucial amounts of heavy elements, enough to fundamentally change the star formation process and allow the creation of smaller, longer-lived stars like our Sun. Our solar system formed from such enriched material approximately 4.5 billion years ago, when a particular region of our galaxy had achieved the chemical diversity necessary for terrestrial planet formation. The gas and dust cloud that collapsed to form the Sun and planets contained not only hydrogen and helium, but also significant amounts of carbon, oxygen, silicon, iron, and dozens of other elements created in previous generations of stars. The calcium in your bones was created when massive stars, many times larger than our Sun, reached the final stages of their nuclear evolution. The fusion reactions that formed these calcium nuclei occurred at temperatures exceeding 1 billion degrees, in stellar cores where the pressure was millions of times greater than Earth's atmospheric pressure. When these stars exploded as supernovae, they scattered their calcium-rich material across thousands of light years, eventually contributing to the formation of new stellar systems, including our own. The iron in your blood carries an even more dramatic history. Most iron atoms were created during the brief moments of core collapse that preceded supernova explosions, when the immense gravitational pressure forced protons and electrons together to form neutrons, releasing the energy that powered the stellar explosion. Every iron atom in your hemoglobin was forged in these conditions of unimaginable extremity, then traveled through space for billions of years before becoming part of the biological machinery that carries oxygen through your body. Even more exotic is the origin of elements like gold and platinum, which require the most extreme nuclear processes to create. Recent observations have confirmed that many of these ultra-heavy elements are produced when neutron stars, the ultra-dense remnants of supernova explosions, collide with each other. These neutron star mergers create conditions even more extreme than supernova, generating intense gravitational waves while simultaneously forging the heaviest elements in the periodic table. The phosphorus essential for DNA and cellular energy storage was created through a complex sequence of nuclear reactions in massive stars, then dispersed through supernova explosions that occurred throughout our galaxy's history. The sulfur that helps proteins maintain their three-dimensional structures formed through oxygen burning in stellar cores, while the trace elements that serve as catalysts in biological reactions were created through various nuclear processes in different types of stars. The timescales involved in this cosmic recycling process are truly staggering. The carbon atoms in your body may have been created in a star that lived and died 8 billion years ago, then spent billions of years traveling through interstellar space before becoming incorporated into the molecular cloud that formed our solar system. These same atoms may have been part of other stars, other planets, or other living organisms during their long cosmic journey. Perhaps most remarkably, this process of stellar nucleosynthesis and dispersal continues today throughout the universe. Every second, somewhere in the cosmos, a massive star reaches the end of its life and explodes as a supernova, creating and dispersing heavy elements that will eventually become part of future planetary systems. The universe is continuously enriching itself with the chemical diversity necessary for complexity and life. This stellar connection means that every person on Earth is quite literally made of ancient starlight, transformed into matter. The electromagnetic radiation that once streamed from stellar surfaces became trapped in atomic nuclei through nuclear fusion processes, then eventually found its way into the molecules that make up your cells, your tissues, and your organs. You are not merely in the universe. You are the universe becoming aware of itself through the atoms forged in stellar cores billions of years ago. As we contemplate this remarkable heritage, we begin to understand that the boundary between living and non-living matter is not as clear as it might initially appear. The atoms that make up your body have been part of countless cosmic processes throughout their billions of years of existence. They have been stellar material, interstellar dust, planetesimal components, atmospheric gases, oceanic constituents, and now biological participants in the ongoing story of cosmic evolution. This ancient stellar heritage connects us not only to the universe's past, but also to its future. The elements in your body will eventually be recycled through Earth's geochemical processes, perhaps becoming part of other living organisms, atmospheric compounds, or geological formations. On even longer timescales, they may be incorporated into future generations of stars, continuing the cosmic cycle of element creation and dispersal that has been operating since the first stellar explosions illuminated the primordial darkness. In recognizing our elemental origins, we glimpse one of the universe's most profound truths: that complexity and beauty can emerge from the most extreme conditions, that creation and destruction are intimately connected, and that every atom in our bodies carries within it the memory of cosmic processes that stretch back to the universe's earliest stellar generations. We are walking libraries of cosmic history, temporary assemblages of ancient starlight that have somehow organized themselves into conscious beings capable of contemplating their own magnificent origins. Gravity's masterwork. Why do galaxies dance, collide, and reshape each other? In the vast expanse of the cosmos, galaxies do not exist in isolation, but participate in an ancient cosmic ballet that has been unfolding for billions of years. These immense collections of stars, gas, and dark matter, each containing hundreds of billions of individual suns, move through space in graceful arcs and spirals, responding to gravitational forces that operate across distances so vast they challenge our ability to comprehend them. The dance of galaxies represents gravity's most magnificent choreography, a slow-motion performance where partners separated by millions of light years influence each other's movements with mathematical precision. Unlike the familiar gravity we experience on Earth, which operates over distances measured in meters or kilometers, galactic gravity works across scales that dwarf our everyday experience, creating interactions that unfold over hundreds of millions of years. This cosmic choreography began in the universe's earliest epochs, when the first galaxies were forming within the invisible scaffolding of the cosmic web. Even as these primordial systems were still assembling themselves from the hydrogen and helium gas of the early universe, they were already beginning to feel the gravitational influence of their neighbors. The same dark matter, halos that provided the gravitational wells for galaxy formation, also determined the pathways along which these newborn galaxies would eventually move. The mathematics governing galactic interactions follows the same fundamental principles that describe planetary orbits, but scaled up to proportions that transform familiar concepts into something almost mystical. When two galaxies approach each other across the cosmic void, their gravitational interaction begins when they are still tens of millions of light years apart. a distance so vast that light from one galaxy takes longer to reach the other than complex life has existed on Earth. As galaxies move closer together, their gravitational dance becomes increasingly intricate. The dark matter halos that surround each galaxy begin to distort and elongate, creating tidal forces that stretch across intergalactic space. These forces are subtle at first, causing only minor perturbations in the outer regions of each galactic system. But they grow stronger with each passing million years as the distance between the galaxies decreases. The process of galactic interaction reveals itself most dramatically in the beautiful spiral arms that characterize disk galaxies like our own Milky Way. These spiral patterns are not permanent structures, but rather temporary waves of compression that propagate through the galactic disk, triggered and shaped by gravitational interactions with neighboring galaxies. As a nearby galaxy approaches, its gravitational influence creates density waves that sweep through the disk, compressing gas clouds and triggering bursts of star formation that illuminate the spiral structure. Perhaps the most spectacular manifestation of galactic gravity occurs when two large galaxies undergo a complete merger. This process, which takes several billion years from initial approach to final coalescence, represents one of the most energetic events in the universe. The gravitational forces involved are so immense that they can reshape entire galactic structures, transforming ordered spiral disks into chaotic stellar streams, and ultimately creating new types of galactic systems altogether. The Andromeda Galaxy, our nearest large galactic neighbor, provides a perfect example of this cosmic choreography in action. Located approximately 2.5 million light-years away, Andromeda is currently approaching the Milky Way at a speed of about 110 kilometers per second. This might seem fast by terrestrial standards, but across the vast distances of intergalactic space, it represents a leisurely approach that will take approximately 4.5 billion years to culminate in a direct collision. When the Milky Way and Andromeda finally merge, the event will showcase gravity's power to reshape galactic architecture on the grandest possible scale. Computer simulations of this future collision reveal a process of extraordinary complexity and beauty, as the two spiral galaxies distort each other's structures through tidal forces, creating long streams of stars that arc across hundreds of thousands of light years. The supermassive black holes at the centers of both galaxies will eventually spiral toward each other, releasing gravitational waves that will ripple through the fabric of space-time itself. The merger process begins long before the galaxies actually interpenetrate each other's stellar populations. As Andromeda approaches, its gravitational influence will trigger changes in the Milky Way's spiral structure, possibly creating new spiral arms, or enhancing existing ones. The outer regions of both galaxies will begin to stretch toward each other, forming what astronomers call tidal tails, streams of stars and gas that extend far beyond the original galactic boundaries. During the most active phase of the merger, both galaxies will lose their organized disk structures as gravitational chaos disrupts the ordered circular orbits of their stars. The resulting system will resemble a cosmic fireworks display, with stars following highly elliptical trajectories that carry them far from their original locations. Despite this apparent chaos, very few individual stars will actually collide with each other, since the distances between stars are enormous even by galactic standards. The final product of the Milky Way-Andromeda merger will be a massive elliptical galaxy, temporarily dubbed Milkomeda by astronomers. This new galactic system will be larger and more massive than either of its parent galaxies, with a smooth, spheroidal distribution of stars and no trace of the beautiful spiral structures that once characterized both systems. But galactic interactions are not limited to dramatic mergers between equal-mass systems. Many of the most interesting gravitational effects occur when large galaxies encounter smaller companions, creating relationships that can persist for billions of years. These interactions showcase gravity's ability to create stable, long-term partnerships between galactic systems of very different masses. The Milky Way itself participates in several such relationships with smaller satellite galaxies. The large and small Magellanic Clouds, visible as fuzzy patches in the southern sky, orbit our galaxy at distances of approximately 160,000 and 200,000 light-years, respectively. These satellite galaxies are slowly losing their gas and stars to the Milky Way's superior gravitational pull, creating streams of material that trace their orbital paths across the sky. The gravitational interaction between the Milky Way and its satellites reveals another aspect of cosmic choreography: the way large galaxies can strip material from smaller companions while simultaneously triggering bursts of star formation within them. As the Magellanic Clouds orbit through the Milky Way's gravitational field, they experience tidal forces that compress their gas clouds, creating ideal conditions for new stellar birth. Galaxy clusters represent the largest gravitationally bound structures in the universe, containing hundreds or thousands of individual galaxies all participating in a complex gravitational dance. Within these clusters, galaxies move at speeds of hundreds or thousands of kilometers per second, following orbits determined by the collective gravitational field of the entire cluster. The resulting interactions create a rich variety of phenomena that demonstrate gravity's ability to organize matter on the largest possible scales. The hot gas that fills the space between cluster galaxies provides another arena where gravitational interactions play out. This intracluster medium, heated to temperatures of tens of millions of degrees by the gravitational energy of cluster formation, creates a tenuous atmosphere that individual galaxies must move through as they orbit within the cluster. The resulting ram pressure can strip gas from galaxies, affecting their ability to form new stars and altering their evolutionary pathways. The role of dark matter in galactic interactions adds another layer of complexity to these cosmic dances. Since dark matter makes up approximately 85% of all matter in the universe, the gravitational interactions between galaxies are dominated by the behavior of this invisible component. Dark matter halos can extend far beyond the visible boundaries of galaxies, creating gravitational influences that operate across much larger distances than would be possible with ordinary matter alone. When galaxies merge, their dark matter halos merge as well, but through a process quite different from the complex gas dynamics and stellar interactions that characterize ordinary matter. Dark matter particles can pass through each other without direct collision, allowing dark matter halos to interpenetrate and gradually settle into new equilibrium configurations. This process helps determine the final structure of merged galactic systems and explains many of the properties we observe in massive elliptical galaxies. The cosmic web itself participates in this gravitational choreography, channeling galaxies along filaments of dark matter that connect the densest regions of the universe. Galaxies do not move randomly through space, but follow preferred pathways determined by the large-scale structure established during the universe's earliest epochs. This cosmic infrastructure continues to guide galactic motions today, directing the flow of matter from less dense regions toward the nodes where galaxy clusters form and grow. The timescales involved in galactic interactions span an enormous range, from the rapid crossing times of galaxies moving through clusters, measured in hundreds of millions of years, to the slow orbital periods of satellite galaxies around larger companions, which can exceed 10 billion years. These vast temporal scales mean that we can observe galactic interactions at every stage of their evolution, from initial approach through final merger, by studying different galactic systems throughout the universe. Modern observations reveal that galactic interactions have been a fundamental driver of cosmic evolution since the earliest epochs of cosmic history. High redshift observations show that galaxy mergers were more common in the early universe, when galaxies were closer together and had not yet had time to move apart due to cosmic expansion. The frequency of interactions has decreased over cosmic time, but the process continues today and will persist as long as galaxies exist. In contemplating the dance of galaxies, we witness gravity operating as both destroyer and creator, dismantling existing structures while simultaneously building new ones. The same force that will eventually merge the Milky Way with Andromeda also maintains the stable orbits that allow stars and planets to exist for billions of years. This cosmic choreography demonstrates that even the most violent astronomical events unfold with mathematical precision, following laws of physics that create beauty and order on scales that encompass the entire observable universe. Solar System Genesis. What strange chain of events formed our cosmic neighborhood? In a quiet corner of the Milky Way, approximately 26,000 light-years from the galactic center, something extraordinary began to unfold 4.5 billion years ago. Within a vast cloud of gas and dust, measuring several light-years across, the delicate balance between pressure and gravity began to shift. This seemingly unremarkable region of space was about to become the birthplace of our solar system, through a series of events so precisely orchestrated that they seem almost impossible in their complexity. The story begins with what astronomers call a molecular cloud, a cold, dark region where temperatures hover just a few degrees above absolute zero. These clouds represent some of the most serene environments in the galaxy, where hydrogen molecules drift through space at velocities measured in mere meters per second. For millions of years, this particular cloud had maintained its equilibrium, with the internal pressure of its gas perfectly balanced against the inward pull of its own gravity. Something disturbed this ancient tranquility. Perhaps it was the shock wave from a nearby supernova explosion, rippling through interstellar space like a stone cast into still water. Or perhaps it was the gravitational influence of a passing star system, stirring the cloud's outer edges with invisible fingers of force. Whatever the trigger, it was sufficient to upset the delicate balance that had maintained the cloud's stability for so long. Once this balance was broken, gravity began its patient work of construction. The cloud's denser regions started to contract, drawing in surrounding material with increasing efficiency. As the gas compressed, it began to warm ever so slightly, but not enough to halt the inexorable process of collapse. The cloud fragmented into smaller clumps, each following its own gravitational destiny. But one particular region would become our future home. Within this contracting region, the laws of physics began to weave a story of remarkable precision. As the cloud collapsed, it began to rotate more rapidly, much like an ice skater spinning faster as they pull their arms closer to their body. This rotation prevented the cloud from collapsing uniformly in all directions, instead flattening it into a rotating disk with a dense central concentration that would eventually become our sun. The transformation from cloud to disk took place over approximately 100,000 years, a remarkably brief moment in cosmic terms. During this period, the temperature at the center of the collapsing region climbed steadily higher, reaching first hundreds, then thousands of degrees. The surrounding disk remained much cooler, creating distinct temperature zones that would prove crucial for determining what types of planets could form at different distances from the nascent star. As the central region continued to contract and heat up, it eventually reached the critical temperature of 10 million degrees Celsius needed to ignite nuclear fusion. In that moment, our sun was truly born, beginning the steady process of converting hydrogen into helium that continues to this day. The ignition of fusion marked a turning point in the solar system's formation, as the new star's energy began to influence the surrounding disk of material in profound ways. The early sun was not the stable, well-behaved star we know today. Young stars are notoriously active, producing powerful stellar winds and intense radiation that can dramatically affect their surroundings. Our infant sun experienced a phase called the T Tauri stage, during which it generated winds so powerful they began to sweep away much of the remaining gas from the inner regions of the disk. This stellar wind acted like a cosmic vacuum cleaner, removing the lighter elements from the inner solar system while leaving behind the heavier, rockier materials that would eventually form the terrestrial planets. Meanwhile, in the cooler outer regions of the disk, a different story was unfolding. Here, beyond what astronomers call the frost line, temperatures were low enough for water to freeze into ice. This created an abundance of solid material that could stick together, providing the building blocks for the massive gas giant planets that would eventually dominate the outer solar system. The process of planet formation began with the accumulation of microscopic dust grains into larger and larger aggregates. These tiny particles, no bigger than the width of a human hair, began to stick together through electrostatic forces and gentle collisions. Over thousands of years, they grew from dust specks to pebbles, from pebbles to boulders, and from boulders to mountain-sized objects called planetesimals. The growth from planetesimals to full-sized planets required a delicate balance of forces. Objects needed to be large enough to attract additional material through their gravitational pull, but not so large that violent collisions would shatter them back into fragments. This process, known as accretion, operated differently in different regions of the solar system, leading to the diverse family of worlds we observe today. In the inner solar system, where temperatures were high and only rocky materials could condense, the planetesimals grew slowly and remained relatively small. The four terrestrial planets, Mercury, Venus, Earth, and Mars, formed through countless collisions between these rocky building blocks. Each impact added mass and generated heat, gradually building worlds that would eventually develop solid surfaces and, in Earth's case, the conditions necessary for life. The formation of Earth involved a particularly dramatic series of events. Early in its history, our planet suffered a catastrophic collision with a Mars-sized object that astronomers have named Theia. This impact was so violent that it nearly destroyed the young Earth, melting its entire surface and ejecting enormous amounts of material into orbit. This debris eventually coalesced to form our moon, creating the Earth-Moon system that has played such a crucial role in maintaining the stable conditions necessary for life's emergence and evolution. Beyond the frost line, where water ice could form, the story unfolded quite differently. Here, the abundance of solid material allowed planetesimals to grow much larger, eventually becoming massive enough to capture and retain the hydrogen and helium gas that still pervaded the outer disk. Jupiter, the first and largest of these gas giants, may have formed in as little as 1 million years once it reached a critical mass of approximately 10 Earth masses. Jupiter's formation had profound consequences for the rest of the solar system. Its immense gravitational influence stirred up the asteroid belt, preventing the formation of a planet between Mars and Jupiter. The giant planet also acted as a gravitational shepherd, protecting the inner solar system from many comets and asteroids that might otherwise have made life's emergence far more difficult. The formation of Saturn, Uranus, and Neptune followed similar patterns, though each developed its own unique characteristics based on its location in the disk and the timing of its formation. These outer giants engaged in complex gravitational interactions that may have caused them to migrate from their original positions, reshuffling the architecture of the outer solar system over millions of years. The final stages of solar system formation were marked by a period of intense bombardment as the remaining planetesimals and debris were swept up by the newly formed planets. This late heavy bombardment, which occurred approximately 4 billion years ago, delivered water and organic compounds to the inner planets while clearing the solar system of most of its remaining construction debris. During this chaotic period, comets from the outer reaches of the solar system rained down on the inner planets, possibly delivering much of Earth's water, and perhaps even some of the organic molecules that would later contribute to the emergence of life. The moon's heavily cratered surface preserves a record of this violent time, showing us just how intense this cosmic cleanup process was. The gravitational dance between the giant planets also sculpted the small body populations that remain in our solar system today. The asteroid belt between Mars and Jupiter contains the leftover building blocks of terrestrial planet formation, while the Kuiper belt beyond Neptune preserves icy remnants from the outer disk. Even more distant, the Oort cloud represents a vast spherical reservoir of comets that extends nearly halfway to the nearest star. What makes our solar system's formation story particularly remarkable is not just the complexity of the processes involved, but their apparent fine-tuning for the eventual emergence of life. The Sun formed with just the right mass to burn steadily for billions of years. Earth formed at just the right distance to maintain liquid water on its surface. Jupiter formed just large enough to protect the inner system without disrupting Earth's orbit. The chemical enrichment of our solar system also tells a story of cosmic recycling that spans billions of years. The heavy elements necessary for rocky planet formation, carbon, oxygen, silicon, iron, were forged in the nuclear furnaces of earlier generations of stars and dispersed into space through supernova explosions. Our solar system formed from material that had been processed through multiple stellar cycles, inheriting a chemical complexity that made the formation of complex worlds possible. The timescales involved in solar system formation remind us of the patience required for cosmic construction projects. While the initial collapse of the molecular cloud took only 100,000 years, the complete formation of the planets required approximately 100 million years. The final cleanup and stabilization of orbital dynamics continued for several 100 million years more. Modern observations of other star-forming regions throughout the galaxy reveal that planetary system formation is a common process. The Hubble Space Telescope has captured images of protoplanetary disks around young stars, showing us solar systems in various stages of construction. These observations confirm that the basic processes that shaped our cosmic neighborhood are universal, operating wherever the right conditions exist. Yet each planetary system develops its own unique characteristics based on the specific details of its formation environment. The mass of the central star, the composition of the original molecular cloud, the presence of nearby stars, and countless other factors all influence the final architecture of each system. This means that while planetary formation follows universal physical laws, the outcomes are endlessly diverse. As we contemplate the chain of events that created our solar system, we're reminded that we live in the product of a 4.5 billion year construction project. Every grain of sand on Earth was once part of that ancient molecular cloud. Every breath we take contains atoms that were forged in stellar cores and dispersed through supernova winds. We are quite literally made of star stuff, connected to the cosmos through the very atoms that comprise our bodies. The story of solar system genesis continues to unfold today, as astronomers discover new details about planetary formation through observations of distant star systems and computer simulations of the early solar system. Each new discovery adds another piece to the puzzle, helping us understand not just how our cosmic neighborhood formed, but how common or rare such systems might be throughout the universe. In this quiet corner of the galaxy, the ancient dance of gravity, chemistry, and physics created something extraordinary, a system of worlds diverse enough to include both the hellish surface of Venus and the delicate balance that makes Earth a haven for life. This remarkable story reminds us that we are part of something much larger than ourselves, participants in a cosmic story that began in the depths of interstellar space and continues to unfold around us every day. Earth's lucky position. How rare is our world? Really? Suspended in the vast darkness of space, our planet Earth occupies a position that seems almost impossibly well suited for life. At first glance, this might appear to be mere cosmic coincidence, one world among billions that happened to find itself in just the right place at just the right time. But as we examine the intricate web of conditions that make our world habitable, we discover a story far more complex and fascinating than simple luck. The concept that has captured the imagination of astronomers and philosophers alike is known as the Goldilocks zone, or more formally, the habitable zone. Like the porridge in the familiar fairy tale, Earth's position around the sun is neither too hot nor too cold, but just right for liquid water to exist on the planetary surface. This zone extends from approximately 93 million miles to 140 million miles from the sun, and Earth sits comfortably within this range at an average distance of 93 million miles. But the habitable zone represents only the beginning of Earth's remarkable story. The temperature at our planet's surface depends not just on our distance from the sun, but on a complex interplay of atmospheric composition, planetary mass, and orbital characteristics that work together to create conditions suitable for life. Without this delicate balance, Earth could easily have become another Venus, with a runaway greenhouse effect that boiled away its oceans, or another Mars, too cold and thin atmosphered to retain liquid water. Our planet's mass plays a crucial role in maintaining these favorable conditions. Earth is large enough to retain a substantial atmosphere through its gravitational pull, yet not so large that it captures and holds on to hydrogen and helium like the gas giant planets. This intermediate size allows Earth to maintain an atmosphere composed primarily of nitrogen and oxygen, with just enough carbon dioxide to create a gentle greenhouse effect that keeps our world warm enough for liquid water. The composition of Earth's atmosphere represents another remarkable aspect of our planet's habitability. The 21% oxygen content provides the perfect balance for complex life, enough to support efficient metabolism in large organisms, but not so much that the atmosphere becomes dangerously flammable. The 78% nitrogen acts as a buffer gas, diluting the oxygen and helping to moderate atmospheric chemistry. This precise atmospheric mixture took billions of years to develop through the complex interactions between geological processes and early life forms. Earth's magnetic field provides another layer of protection that makes complex life possible. Generated by the motion of molten iron in our planet's core, this invisible shield deflects most of the harmful charged particles streaming from the sun as solar wind. Without this protection, our atmosphere would gradually be stripped away, as appears to have happened to Mars over billions of years. The strength and stability of Earth's magnetic field depend on the continuing activity of our planet's molten core, which is maintained by the heat generated through radioactive decay of elements like uranium and thorium. The presence of our moon adds yet another element to Earth's habitability story, far larger relative to its parent planet than most moons in the solar system. Our lunar companion stabilizes Earth's rotational axis, preventing dramatic climate swings that might otherwise make long-term evolution difficult. The moon's gravitational influence also creates tides that may have played an important role in the early development of life, creating tidal pools where organic molecules could concentrate and interact. Our planet's orbit around the sun exhibits a nearly circular path, with an eccentricity of only about 0.017. This means that Earth receives a relatively constant amount of solar energy throughout the year, avoiding the extreme seasonal variations that would result from a highly elliptical orbit. Many exoplanets discovered around other stars have much more eccentric orbits, subjecting them to temperature swings that would make the development of stable ecosystems extremely challenging. The tilt of Earth's rotational axis at approximately 23.5 degrees creates our seasonal cycles while avoiding the extreme temperature variations that would result from a much larger tilt. This axial tilt, stabilized by the moon's gravitational influence, ensures that neither of Earth's poles remains in permanent darkness or permanent sunlight for extended periods, helping to moderate global climate patterns. Earth's position within the solar system offers protection from cosmic hazards that might otherwise threaten life's development. Jupiter's immense gravitational influence acts as a cosmic vacuum cleaner, capturing or deflecting many comets and asteroids that might otherwise impact Earth. While some impacts do occur and have played important roles in Earth's history, Jupiter's presence significantly reduces the frequency of potentially catastrophic collisions. The chemical composition of Earth reflects another aspect of our planet's special nature. Our world formed from material that had been enriched with heavy elements through multiple generations of stellar nucleosynthesis. This chemical complexity provides the diverse building blocks necessary for complex chemistry and life. Elements like carbon, oxygen, nitrogen, phosphorus, and sulfur are abundant enough to support the intricate molecular machinery of living organisms. Earth's geological activity contributes to habitability through the process of plate tectonics. The slow movement of crustal plates recycles carbon dioxide between the atmosphere and Earth's interior, helping to regulate global temperature through the carbonate-silicate cycle. This geological thermostat has helped maintain relatively stable surface temperatures over billions of years, despite the gradual increase in the sun's luminosity over geological time. The timing of Earth's formation also appears to have been fortuitous. Our planet formed early enough in the galaxy's history to benefit from heavy element enrichment from previous stellar generations, but late enough to avoid the more chaotic conditions that prevailed in the galaxy's youth, when supernova explosions and other violent events were more common. This timing placed Earth in what some astronomers call the galactic habitable zone. Water, that most essential ingredient for life, as we know it, exists in all three phases on Earth's surface: solid, liquid, and gas. This remarkable substance covers approximately 71% of our planet's surface and plays countless roles in maintaining habitability. Water's unique properties, including its high heat capacity and its expansion when frozen, help moderate Earth's climate and protect aquatic life during cold periods. The presence of continental landmasses adds another dimension to Earth's habitability. The arrangement of continents and oceans influences global climate patterns through ocean currents and atmospheric circulation. The current configuration, with landmasses distributed across various latitudes, helps moderate global temperatures and creates diverse climate zones that support a wide variety of ecosystems. Earth's rotation period of 24 hours creates a day-night cycle that allows for temperature moderation, while providing enough energy gathering time for photosynthetic organisms. A much faster rotation would create extreme weather patterns, while much slower rotation would lead to extreme temperature differences between day and night sides of the planet. The question of how rare Earth-like conditions might be in the universe continues to challenge astronomers and astrobiologists. The discovery of thousands of exoplanets has revealed the incredible diversity of planetary systems, with many configurations quite different from our own solar system. Some planets orbit much closer to their stars, locked in synchronous rotation with permanent day and night sides. Others follow highly eccentric orbits or exist in multiple star systems with complex gravitational dynamics. Recent observations have identified several potentially habitable exoplanets, worlds that appear to orbit within their star's habitable zone and may possess some Earth-like characteristics. However, determining whether these distant worlds truly possess the complex combination of factors that make Earth habitable remains beyond our current observational capabilities. The presence of water vapor, oxygen, or other biosignatures in exoplanet atmospheres represents the cutting edge of current research. The concept of planetary habitability continues to evolve as we learn more about extremophile organisms on Earth that thrive in conditions once thought to be incompatible with life. These discoveries have expanded our understanding of the potential habitable zone and suggested that life might be possible under a broader range of conditions than previously imagined. Subsurface oceans on moons like Europa and Enceladus demonstrate that habitable environments might exist far beyond traditional habitable zones. The anthropic principle offers one perspective on Earth's apparent fine-tuning for life. This philosophical concept suggests that we observe these favorable conditions precisely because they were necessary for our existence. In a universe with countless planets, we naturally find ourselves on one of the rare worlds where conditions allow for complex life and intelligence to develop. Alternative scenarios help us appreciate just how special Earth's conditions are. If Earth were just 5% closer to the Sun, the increased heat might have triggered a runaway greenhouse effect similar to Venus. If our planet were just 15% farther away, it might have remained frozen like Mars, with any water locked away as ice. These narrow margins highlight the precision required for long-term habitability. The stability of Earth's conditions over geological time represents perhaps the most remarkable aspect of our planet's story. Despite massive changes in solar luminosity, atmospheric composition, and continental configuration over 4.5 billion years, Earth has maintained conditions suitable for liquid water and life. This stability suggests the operation of complex feedback mechanisms that help regulate global climate and chemistry. Looking toward the future, Earth's habitability will not remain constant forever. As the Sun gradually increases in luminosity over the next billion years, our planet will eventually become too hot to maintain liquid water on its surface. The ongoing evolution of the Sun will ultimately push Earth beyond the habitable zone, ending our planet's long tenure as an oasis for life. Current research into planetary habitability combines observations of exoplanets with detailed climate modeling and studies of Earth's own history. Scientists are working to understand which factors are truly essential for habitability and which might be less critical than previously thought. This research will help guide future searches for potentially habitable worlds and inform our understanding of life's prospects throughout the universe. The search for life beyond Earth has become one of the defining scientific quests of our time. Advanced telescopes currently under development will soon be capable of analyzing the atmospheric compositions of Earth-sized exoplanets, potentially detecting the chemical signatures of biological processes. These observations may finally answer the question of whether Earth-like worlds are common or extraordinarily rare in the cosmic community. As we contemplate Earth's position in the universe, we are reminded that our world represents the culmination of billions of years of cosmic evolution. The elements in our bodies were forged in stellar cores. The energy that drives our climate comes from nuclear fusion in the Sun's core, and the very existence of our planet depends on the gravitational dynamics that shaped our solar system. We are part of an unbroken chain of cosmic evolution that connects us to the deepest structures of space and time. Whether Earth's combination of habitability factors is common or rare remains one of the great unanswered questions in science. What we do know is that our planet represents a remarkable sanctuary for life in the vast cosmos. A world where chemistry became biology, and simple organisms evolved into complex ecosystems capable of contemplating their own existence. In this quiet corner of the universe, the conditions for life found their perfect expression, creating a world that continues to inspire wonder and scientific inquiry. The expanding universe. Why is space stretching faster and faster, and where is it going? In the early decades of the 20th century, astronomers made a discovery that fundamentally changed our understanding of the cosmos. The universe, which had long been thought of as static and unchanging, was revealed to be expanding. Every galaxy beyond our local group is moving away from us, and the farther away they are, the faster they appear to be receding. This expansion is not happening because galaxies are moving through space, but because space itself is stretching, carrying distant galaxies along with it like raisins in rising bread dough. The story of this remarkable discovery begins with the work of astronomer Edwin Hubble in the 1920s. Using the newly constructed Mount Wilson telescope, Hubble measured the distances to nearby galaxies and observed their light through spectroscopy. What he found was that the light from distant galaxies appeared shifted toward the red end of the spectrum, indicating that these galaxies were moving away from us. More surprisingly, he discovered that this redshift increased with distance, a relationship now known as Hubble's law. This cosmic expansion represents one of the most profound concepts in modern astronomy. When we say that space is expanding, we mean that the fundamental fabric of space-time itself is stretching. Imagine a balloon with dots drawn on its surface representing galaxies. As the balloon inflates, the dots move apart from each other, but they are not moving across the balloon's surface. Instead, the surface itself is expanding, carrying the dots along with it. This analogy helps us understand how galaxies can recede from each other without actually traveling through space. The rate of this expansion is quantified by the Hubble constant, which describes how quickly space expands at different scales. Current measurements suggest that for every megaparsec of distance, approximately 3.3 million light-years, space expands at a rate of about 70 kilometers per second. This means that a galaxy located 100 million light-years away is receding from us at approximately 2,100 kilometers per second. Not because it is moving through space at that speed, but because the space between us and that galaxy is expanding. The expansion of the universe naturally leads us to consider its history. If space is expanding today, then it must have been smaller in the past. Tracing this expansion backward in time brings us to a moment approximately 13.8 billion years ago, when all of space was compressed into an infinitesimally small point. This moment marks what we call the Big Bang, though this term is somewhat misleading since it was not an explosion in space, but rather the beginning of space and time themselves. During the universe's earliest moments, expansion occurred at an almost unimaginable rate. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called cosmic inflation. During this brief interval, space expanded faster than the speed of light, growing from subatomic to astronomical scales in less time than it takes light to cross a proton. This inflationary period helps explain many of the universe's observed properties, including its remarkable uniformity on large scales. As the universe continued to expand and cool, the fundamental forces of physics began to separate from their unified state. The strong nuclear force, which holds atomic nuclei together, separated first, followed by the weak nuclear force responsible for certain types of radioactive decay. The electromagnetic force, which governs the behavior of charged particles, emerged as temperatures dropped further. Gravity, the weakest but most far-reaching of the fundamental forces, had separated much earlier, during the first moments of inflation. The early universe was filled with a hot, dense soup of elementary particles and radiation. As expansion continued and temperatures dropped, these particles began to combine into the first atomic nuclei during a period called Big Bang nucleosynthesis. This process, occurring during the first few minutes after the Big Bang, created the light elements we observe today, primarily hydrogen and helium, with trace amounts of lithium and beryllium. The relative abundances of these elements provide crucial evidence supporting our understanding of cosmic expansion and the Big Bang model. For approximately 380,000 years after the Big Bang, the universe remained opaque to light. Free electrons scattered photons continuously, preventing light from traveling far through space. But as the universe expanded and cooled further, electrons and protons combined to form neutral hydrogen atoms in an event called recombination. Suddenly, space became transparent and light could travel freely across cosmic distances. This ancient light, stretched by billions of years of cosmic expansion, still permeates the universe today as the cosmic microwave background radiation. The universe's expansion has not proceeded at a constant rate throughout cosmic history. During the radiation-dominated era, when photons and other massless particles provided most of the universe's energy density, expansion decelerated due to the gravitational attraction of matter and energy. Later, as the universe grew larger and matter became more dilute, the expansion rate continued to slow, though more gradually. However, observations in the late 20th century revealed a startling discovery. By studying distant supernovae, astronomers found that the universe's expansion is not slowing down as expected, but is actually accelerating. This acceleration appears to have begun approximately 5 billion years ago, when the universe was roughly half its current age. The cause of this acceleration has been attributed to a mysterious component called dark energy. Dark energy represents one of the greatest puzzles in modern cosmology. It appears to make up approximately 68% of the universe's total energy density, yet its nature remains completely unknown. Unlike matter, which clumps together under gravitational attraction, dark energy appears to have a repulsive effect, driving the acceleration of cosmic expansion. The simplest explanation is that dark energy represents the energy inherent in space itself, a cosmological constant that maintains a uniform density even as space expands. The implications of accelerating expansion are profound for the universe's future. If dark energy continues to dominate cosmic evolution, the universe will expand forever, growing colder and more dilute with time. Galaxies beyond our local group will eventually disappear beyond our observable horizon. Carried away by the stretching of space itself, stars will continue to form and burn out. But the raw materials for new star formation will become increasingly sparse as gas clouds are dispersed by expansion. The observable universe represents the region of space from which light has had time to reach us since the Big Bang. This sphere, centered on Earth, has a radius of approximately 46.5 billion light-years, despite the universe being only 13.8 billion years old. This apparent contradiction results from the expansion of space itself, which has carried the sources of the most distant light far beyond their original positions when that light was emitted. Beyond the observable universe lies the larger, possibly infinite expanse of the entire universe. We cannot observe this region directly, but the laws of physics suggest that it likely contains the same types of structures we see within our observable sphere: galaxies, stars, and planets distributed in the same cosmic web of dark matter that we observe nearby. The expansion of space ensures that we will never be able to observe these distant regions, no matter how long we wait or how advanced our technology becomes. The cosmic expansion also affects our understanding of distance and time in the universe. Light from distant galaxies was emitted when the universe was younger and more compact. When we observe a galaxy 10 billion light-years away, we see it as it existed 10 billion years ago, when the universe was less than 4 billion years old. This means that our telescopes function as time machines, allowing us to observe the universe's history directly by looking at increasingly distant objects. The expansion of space creates a fundamental horizon beyond which we cannot observe or influence events. This cosmic horizon is constantly growing as light from more distant regions has time to reach us. But it also represents a fundamental limit to our knowledge of the universe. Objects currently located beyond this horizon will remain forever inaccessible to us, existing in a realm that is causally disconnected from our own. Modern measurements of cosmic expansion rely on increasingly sophisticated techniques and observations. Type Ia supernovae serve as standard candles, providing precise distance measurements to galaxies billions of light-years away. The cosmic microwave background radiation, offers a snapshot of the universe when it first became transparent, allowing astronomers to measure the expansion rate and composition of the early cosmos. Gravitational waves from merging black holes and neutron stars provide yet another method for measuring cosmic distances and expansion rates. The expansion of the universe raises fundamental questions about the nature of space and time themselves. Einstein's general theory of relativity describes gravity not as a force, but as the curvature of space-time caused by matter and energy. In this framework, the expansion of the universe represents the evolution of space-time geometry itself, driven by the matter and energy it contains. Current observations suggest that the universe's geometry is very close to flat, meaning that parallel lines remain parallel even over cosmic distances. This flatness is maintained despite the universe's expansion and represents one of the remarkable fine-tuning aspects of our cosmos. A universe that was significantly curved would have either collapsed back on itself or expanded so rapidly that stars and galaxies could never have formed. The concept of cosmic expansion challenges our everyday intuitions about space and motion. We are accustomed to thinking of space as a fixed stage on which events unfold, but cosmic expansion reveals space itself to be dynamic and evolving. This expansion does not occur within some larger container, but represents the fundamental evolution of reality itself. As we contemplate the expanding universe, we are reminded of our place within this grand cosmic story. The atoms in our bodies were forged in stellar cores that formed as the universe expanded and cooled from its hot, dense beginning. The galaxies we observe in the night sky are participants in this cosmic expansion, carried along by the stretching of space itself. We exist within an evolving cosmos, one that began in unimaginable heat and density and continues to expand toward an uncertain but fascinating future. The study of cosmic expansion continues to reveal new mysteries and deepen our understanding of the universe's fundamental nature. As our observational techniques improve and our theoretical understanding advances, we edge closer to answering some of the most profound questions about existence itself. In this expanding cosmos, we find both our origins and our destiny, written in the language of physics across the vast scales of space and time. Cosmic background echo. What ancient light still whispers the universe's origin story? Permeating every cubic centimeter of space around us, invisible to our eyes but detectable by sensitive instruments, lies the oldest light in the universe. This ancient radiation carries within it the whispered secrets of cosmic creation, a message transmitted across 13.8 billion years of space and time. Known as the cosmic microwave background, this gentle glow represents the afterglow of the Big Bang itself, stretched and cooled by eons of cosmic expansion into a faint echo that tells the story of our universe's birth. The cosmic microwave background radiation was not always the cool, barely detectable signal we observe today. In the universe's infancy, this same radiation blazed with the intensity of stellar surfaces, filling all of space with light hot enough to prevent the formation of atoms. For nearly 400,000 years after the Big Bang, the universe remained a glowing plasma where electrons and protons moved freely, scattering photons in an endless cosmic pinball game that kept space opaque to light. This era, known as the photon epoch, was a time when matter and radiation remained in thermal equilibrium. Every photon that tried to travel through space was quickly absorbed and re-emitted by free electrons, creating a cosmic fog that prevented light from journeying more than a few centimeters before being scattered in a new direction. The universe was brilliant beyond imagination, yet this brilliance was trapped, unable to travel the vast distances that would later allow galaxies to see each other across cosmic voids. As the universe continued its relentless expansion, temperatures gradually declined. When the cosmic temperature dropped to approximately 3,000 degrees Kelvin, something remarkable occurred. Electrons and protons, which had been kept apart by the intense heat and radiation pressure, finally possessed little enough energy to combine into neutral hydrogen atoms. This process, called recombination, fundamentally changed the nature of space itself. With most electrons now bound to protons and neutral atoms, photons suddenly found themselves free to travel unimpeded through the universe. In a cosmic instant, space transformed from opaque to transparent. releasing a flood of light that had been trapped since the universe's earliest moments. This light, emitted from every point in space simultaneously, began its journey across the expanding cosmos, carrying with it a snapshot of the universe as it existed at that pivotal moment. The discovery of this cosmic background radiation ranks among the most important scientific achievements of the 20th century. In 1965, radio astronomers Arno Penzias and Robert Wilson detected an unexpected signal while calibrating a sensitive antenna at Bell Laboratories. No matter which direction they pointed their instrument, they found the same faint radio noise, constant and uniform, across the entire sky. Initially puzzled by this persistent signal, which they initially attributed to equipment problems, or even interference from pigeons nesting in their antenna, Penzias and Wilson had stumbled upon evidence for the Big Bang theory. The radiation they detected matched precisely the predictions of cosmologists who had theorized that such an afterglow should exist if the universe had indeed emerged from a hot, dense beginning. The cosmic microwave background appears remarkably uniform when viewed across the entire sky, maintaining nearly the same temperature and intensity in all directions. This uniformity represents one of the most striking features of our universe, suggesting that the early cosmos was extraordinarily smooth and well mixed. The temperature variations across different regions of the sky amount to only a few millionths of a degree, a uniformity that would be difficult to achieve unless the early universe underwent a period of rapid expansion that stretched quantum fluctuations to cosmic scales. However, this near-perfect uniformity contains within it the seeds of cosmic structure. Tiny temperature variations in the cosmic microwave background, detected by increasingly sensitive instruments, reveal density fluctuations that existed when the universe first became transparent. These minute irregularities, caused by quantum fluctuations during the universe's inflationary epoch, would eventually grow under the influence of gravity to become the galaxies, stars, and planets we observe today. The cosmic microwave background radiation has been stretched by billions of years of cosmic expansion. What began as visible light with wavelengths similar to sunlight has been redshifted into the microwave portion of the electromagnetic spectrum. The radiation now peaks at a wavelength of approximately 1.9 millimeters, corresponding to a temperature of just 2.7 degrees above absolute zero. This cooling represents one of the most direct pieces of evidence for cosmic expansion. As space itself stretches, it carries the wavelengths of photons along with it, gradually shifting them toward longer, redder wavelengths. The current temperature of the cosmic microwave background provides a precise measurement of how much the universe has expanded since the epoch of recombination, confirming our understanding of cosmic evolution over the past 13.8 billion years. Modern satellites and ground-based telescopes have mapped the cosmic microwave background with extraordinary precision, revealing its structure in exquisite detail. The Cosmic Background Explorer satellite, launched in 1989, first detected the tiny temperature variations that would later be mapped with increasing accuracy by subsequent missions. The Wilkinson Microwave Anisotropy Probe and the Planck satellite have created detailed maps of these fluctuations, providing cosmologists with a baby picture of the universe. These temperature maps reveal patterns that encode information about the fundamental properties of the universe. The size and distribution of hot and cold spots in the cosmic microwave background depend on the universe's geometry, its rate of expansion, and the relative amounts of ordinary matter, and dark energy it contains. By analyzing these patterns, cosmologists can determine cosmic parameters with remarkable precision, treating the cosmic microwave background as a vast cosmic laboratory. The acoustic oscillations visible in the cosmic microwave background provide particularly valuable information about the early universe. Before recombination, pressure waves traveled through the hot plasma at approximately 60% the speed of light, creating regions of compression and rarefaction. When recombination occurred, these sound waves were frozen into the pattern of temperature fluctuations we observe today, providing a fossil record of acoustic processes in the primordial plasma. The polarization of cosmic microwave background radiation offers additional insights into the universe's early history. Light becomes polarized when it scatters off electrons, And the pattern of polarization in the cosmic background radiation can reveal information about the motion and distribution of matter during the recombination epoch. Some theories predict that gravitational waves from cosmic inflation should have left distinctive polarization signatures in the cosmic microwave background, though these signals remain extremely difficult to detect. The cosmic microwave background also provides a unique reference frame for measuring motion through the universe. Because this radiation is nearly uniform in all directions, any motion relative to it creates a small temperature difference between the direction of motion and the opposite direction. Observations reveal that our solar system is moving at approximately 370 kilometers per second relative to the cosmic microwave background carried along by the motion of the Milky Way galaxy through space. The study of cosmic microwave background radiation has revolutionized our understanding of cosmology, transforming it from a largely speculative field into a precision science. The exquisite measurements possible with modern instruments allow cosmologists to test theoretical models with unprecedented accuracy, leading to the current standard model of cosmology known as lambda-CDM, which describes a universe composed of ordinary matter, dark matter, and dark energy. The temperature fluctuations in the cosmic microwave background represent the quantum mechanical uncertainties of the very early universe, amplified to cosmic scales by inflation and preserved as a record in the ancient light. These fluctuations, generated by quantum processes when the universe was smaller than a subatomic particle, eventually grew to become the largest structures we observe today. The cosmic microwave background thus provides a direct connection between the quantum world and the cosmic scale. Future observations of the cosmic microwave background may reveal even more subtle effects, potentially including signatures of cosmic strings, primordial magnetic fields, or other exotic phenomena from the early universe. Advanced polarization measurements might detect the gravitational wave background from inflation, providing direct evidence for this crucial period in cosmic history. Each new observation adds another layer to our understanding of the universe's origin and evolution. The cosmic microwave background radiation serves as a cosmic time capsule, preserving information about conditions when the universe was only a few 100,000 years old. Unlike starlight, which can be absorbed, scattered, or blocked by intervening matter, the cosmic background radiation reaches us directly from the era of recombination, providing an unobstructed view of the early universe that no other astronomical observation can match. The nearly perfect blackbody spectrum of the cosmic microwave background confirms that matter and radiation were once in thermal equilibrium throughout the universe. This observation supports the hot Big Bang model and rules out alternative theories that might produce similar expansion without the high temperature phase required to create such a perfect thermal spectrum. The existence of the cosmic microwave background radiation also has philosophical implications for our understanding of the universe. This ancient light demonstrates that we live in a universe with a definite beginning, one that has evolved from a hot, dense state to its current cool, expanded condition. The radiation provides tangible evidence that the entire observable universe was once compressed into a region smaller than a single atom. The cosmic microwave background continues to expand our horizons in unexpected ways. Recent observations have revealed that this ancient radiation can be used to study the evolution of galaxy clusters through a phenomenon called the Sunyaev-Zeldovich effect, where hot gas in clusters slightly distorts the spectrum of background radiation passing through them. This technique allows astronomers to detect distant clusters and study their properties in ways that complement traditional optical and X-ray observations. As we contemplate this ancient light that surrounds us, we are reminded that we exist within the aftermath of creation itself. Every cubic centimeter of space carries within it photons that have traveled for nearly 14 billion years, bringing us news of the universe's birth. These photons have witnessed the formation of the first stars and galaxies, the birth of our solar system, and the emergence of life on Earth, all while maintaining their journey through the expanding cosmos. The cosmic microwave background radiation represents perhaps the most direct connection we have to the universe's beginning. In detecting and studying this ancient light, we are literally observing the afterglow of creation, reading the story of cosmic origins written in the language of electromagnetic radiation, across the vast scales of space and time. This faint whisper from the past continues to inform our understanding of where we came from and where the universe is heading, carrying within it the secrets of cosmic dawn. Before the beginning, could something have existed before the Big Bang? The question of what existed before the Big Bang touches upon one of the most profound mysteries in all of science and philosophy. For most of human history, the concept of a beginning to time itself seemed almost incomprehensible. Yet modern cosmology suggests that our universe, along with space and time as we understand them, emerged from a singular moment approximately 13.8 billion years ago. This leaves us with a question that challenges the very foundations of causality and existence. If time itself began with the Big Bang, what meaning can we assign to the concept of before? Traditional physics treats the Big Bang as a boundary beyond which our current understanding breaks down completely. At this moment, known as the Planck time, approximately 10 to the power of negative 43 seconds after the beginning, the known laws of physics cease to provide meaningful descriptions of reality. Before this threshold, temperatures and densities become so extreme that quantum effects and gravitational forces merge in ways that our current theories cannot adequately describe. The challenge of discussing anything before the Big Bang lies partly in the nature of time itself. According to Einstein's general theory of relativity, time is not a universal constant, but rather a dimension intricately woven together with space to form the fabric of space-time. If the Big Bang represents the beginning of this space-time fabric, then asking what came before becomes analogous to asking what lies north of the North Pole, a question that may be fundamentally meaningless within our current framework of understanding. However, theoretical physicists have not been deterred by these conceptual barriers. Several sophisticated theories attempt to describe conditions before the Big Bang, or to place our universe within a larger cosmic context, where the Big Bang represents not a true beginning, but rather a transition between different states of existence. These theories push the boundaries of human imagination, while remaining grounded in mathematical rigor and observational possibility. One of the most intriguing approaches to this question involves the concept of cosmic inflation, which describes a period of exponential expansion during the universe's first moments. While inflation explains many observed properties of our universe, it also raises new questions about what triggered this inflationary period and what conditions existed before it began. Some versions of inflationary theory suggest that inflation may be an eternal process, constantly creating new regions of space that undergo their own Big Bang-like transitions. In this eternal inflation scenario, our observable universe represents just one bubble in an infinite foam of expanding regions, each with potentially different physical laws and constants. The Big Bang that created our universe would then be merely one event in an ongoing process of cosmic creation, with new universes constantly being born from the quantum fluctuations of an ever-expanding inflationary background. This perspective transforms the Big Bang from a unique beginning into one episode in an eternal cosmic story. Quantum mechanics adds another layer of complexity to questions about cosmic origins. At the quantum level, the distinction between existence and non-existence becomes blurred by the fundamental uncertainty that governs all microscopic processes. Quantum fluctuations can briefly create particle-antiparticle pairs from apparently empty space, suggesting that even nothingness possesses a complex underlying structure. Some theories propose that the entire universe emerged from such a quantum fluctuation, growing from a microscopic seed into the vast cosmos we observe today. The concept of quantum tunneling offers another perspective on cosmic origins. Just as quantum particles can tunnel through energy barriers that would be insurmountable in classical physics, some theories suggest that the universe itself may have tunneled from a state of non-existence into existence. This quantum creation scenario removes the need for any pre-existing conditions, proposing instead that the universe spontaneously emerged from the quantum vacuum through purely probabilistic processes. String theory, one of the most ambitious attempts to unify quantum mechanics with gravity, provides yet another framework for considering pre-Big Bang scenarios. In string theory, the fundamental constituents of reality are not point particles, but rather tiny vibrating strings existing in a space with more than the three dimensions we observe. Some string theory models describe cosmological scenarios where our universe is embedded in a higher dimensional space called the bulk, where other universes or branes might exist. These higher dimensional models suggest various ways that our universe might have originated through interactions between branes in the bulk space. In some scenarios, the Big Bang resulted from a collision between branes, while others propose that our universe budded off from a pre-existing brane structure. These theories potentially allow for rich physics before our Big Bang, occurring in dimensions beyond our direct observation, but nonetheless influencing the conditions that led to our universe's birth. The cyclic universe models represent another approach to the question of cosmic origins. These theories suggest that our universe undergoes endless cycles of expansion and contraction, with each Big Bang followed eventually by a big crunch that sets the stage for the next cycle. In this framework, our current universe represents just one phase in an eternal oscillation between states of maximum expansion and compression. Modern versions of cyclic cosmology avoid some of the problems that plagued earlier oscillating universe models. Rather than requiring the universe to collapse under its own gravity, these newer theories incorporate the observed acceleration of cosmic expansion in ways that could potentially lead to future transitions between expansion and contraction phases. The dark energy that currently drives accelerating expansion might undergo changes that reverse its effects, eventually leading to a new epoch of cosmic evolution. Loop quantum cosmology, which applies quantum mechanical principles to the large-scale structure of space-time itself, suggests that the Big Bang may have been preceded by a big bounce from a previously contracting universe. In this scenario, quantum effects prevent the universe from collapsing to a true singularity, instead causing it to bounce back into an expansion phase. The Big Bang becomes not a moment of creation, but rather a transition point between cosmic contraction and expansion. The multiverse hypothesis extends these ideas even further, suggesting that our universe exists within a vast ensemble of universes, each with potentially different physical laws and constants. In some multiverse models, new universes are constantly being created through various mechanisms, from quantum fluctuations to black hole formation. Our Big Bang would represent just one birth event in an infinite population of universes, each with its own history and future evolution. These multiverse scenarios raise profound questions about the nature of existence and reality. If infinitely many universes exist with all possible combinations of physical laws and initial conditions, then every conceivable type of universe must exist somewhere within the multiverse. This perspective, while scientifically intriguing, also challenges our ability to make meaningful statements about cosmic uniqueness or fine-tuning. The philosophical implications of pre-Big Bang scenarios extend beyond physics into questions about causality, existence, and the nature of reality itself. If our universe emerged from quantum processes in a larger multiverse, what determined the specific properties we observe? How do we understand concepts like probability and natural selection when applied to entire universes? These questions push us toward new ways of thinking about existence that may require fundamental revisions to our philosophical frameworks. Observational cosmology continues to search for evidence that might constrain or support various pre-Big Bang scenarios. The cosmic microwave background radiation preserves information about the universe's earliest accessible moments, and future observations may reveal signatures of pre-Big Bang physics. Gravitational waves, ripples in space-time itself, might carry information from cosmic epochs even earlier than the surface of last scattering that produced the microwave background. The study of cosmic inflation has revealed tantalizing hints about pre-Big Bang conditions. The nearly scale-invariant spectrum of density fluctuations observed in the cosmic microwave background matches predictions of inflationary models, but the specific details of this spectrum might encode information about the physics that triggered inflation. Future observations with greater precision may reveal whether inflation was preceded by other physical processes or emerged from more fundamental quantum gravitational effects. Some theories predict that pre-Big Bang scenarios should leave observable consequences in the current universe. Cyclic models might produce specific patterns in the cosmic microwave background or the distribution of galaxies, Brain collision scenarios could generate gravitational wave signatures detectable by future space-based observatories. String theory landscapes might predict certain ranges for fundamental constants that could be tested against observations. The question of cosmic origins also intersects with our understanding of consciousness and observation. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in determining physical reality. In this context, the emergence of conscious observers in our universe might be connected to the specific conditions that led to the Big Bang, creating a deep relationship between mind and cosmic origin that transcends traditional scientific categories. As we contemplate these possibilities, we find ourselves at the intersection of science and philosophy, where the most fundamental questions about existence meet the most advanced mathematical theories. The question of what existed before the Big Bang may ultimately be unanswerable within our current scientific framework, or it may require conceptual breakthroughs that fundamentally alter our understanding of time, space, and causality. Whether our universe emerged from eternal inflation, quantum tunneling, brain collisions, or some other exotic process, the exploration of these possibilities expands our imagination and deepens our appreciation for the mystery of existence. Each theoretical framework offers a different perspective on the ultimate nature of reality, reminding us that our universe, remarkable as it is, may be part of something even more extraordinary than we can currently comprehend. The search for answers to pre-Big Bang questions continues to drive advances in theoretical physics and observational cosmology. While we may never know with certainty what preceded our cosmic beginning, the attempt to understand these ultimate questions enriches our scientific knowledge and philosophical wisdom. In contemplating the possibility of existence before the beginning, we engage with mysteries that connect us to the deepest aspects of reality itself. The calm after creation. What does the universe's birth teach us about existence itself? As we reach the end of our journey through cosmic origins, we find ourselves in a place of quiet contemplation. We have traveled from the first moments of creation, through the mysterious possibilities of what might have existed before the beginning. And now, we arrive at perhaps the most profound question of all. What does the universe's birth teach us about the nature of existence itself? The story of cosmic creation, in all its theoretical complexity and observational wonder, offers us something more than scientific knowledge. It provides a mirror in which we can examine our own place in the vast tapestry of reality. When we consider the emergence of space and time from conditions beyond our current understanding, we are confronted with the fundamental mystery of why anything exists at all. The universe's birth reveals to us the extraordinary nature of ordinary existence. In a cosmos that could have remained empty, devoid of matter, energy, or structure, something remarkable occurred. From quantum fluctuations emerged the seeds of galaxies. From primordial plasma came the atoms that would eventually form stars, planets, and life itself. This transformation from simplicity to complexity, from uniformity to diversity, speaks to an underlying creative principle that operates at every scale of reality. Consider the delicate balance that characterizes our universe. The fundamental constants of nature, the strength of gravity, the electromagnetic force, the masses of elementary particles, all exist within narrow ranges that allow for the formation of stable atoms, molecules, and ultimately the complex chemistry of life. Had these values been slightly different, our universe might have collapsed immediately after the Big Bang, or expanded so rapidly that no structures could ever form. This cosmic fine-tuning invites us to contemplate the relationship between possibility and actuality. Among all the ways the universe could have unfolded, we find ourselves in one where consciousness can emerge and reflect upon its own origins. Whether this represents extraordinary coincidence, fundamental necessity, or selection from an infinite multiverse of possibilities, it suggests that our existence is far from inevitable or trivial. The birth of the universe also teaches us about the nature of time itself. Before cosmic creation, time as we understand it did not exist. The Big Bang marked not just the beginning of matter and energy, but the beginning of temporal flow, of cause and effect, of the very possibility of change and development. This perspective transforms our understanding of beginnings and endings, suggesting that time itself is not an eternal stage upon which events unfold, but rather an emergent property of the universe's existence. In contemplating cosmic origins, we encounter the limits of human language and conceptual frameworks. Our everyday experience provides us with intuitions about space, time, and causality that break down when applied to the universe's first moments. We speak of temperatures of 10 to the power of 32 Kelvin, densities approaching infinity, and time intervals measured in units of 10 to the power of -3 power of -43 seconds. These numbers stretch our imagination to its breaking point, reminding us that reality extends far beyond the realm of direct human experience. Yet, within these extreme conditions, we find the seeds of familiarity. The hydrogen and helium nuclei forged in the universe's first few minutes eventually became the raw materials for the first stars. Those stars, through nuclear fusion in their cores, created the heavier elements that would later form rocky planets and biological molecules. Carbon, oxygen, nitrogen, and iron, the elements essential for life, were literally cooked in stellar furnaces and dispersed through space by supernova explosions. This cosmic alchemy connects us directly to the universe's birth. Every atom in our bodies, except for hydrogen, was created either in the Big Bang nucleosynthesis or within the heart of a dying star. We are not separate from the cosmos, but rather a natural expression of its creative potential. The same physical laws that govern the universe's first moments continue to operate within our cells, our thoughts, and our dreams. The emergence of complexity from simplicity represents one of the most remarkable aspects of cosmic evolution. From the nearly uniform distribution of matter in the early universe arose the rich structure we observe today. Galaxies arranged in vast filaments and walls, separated by enormous cosmic voids. Within galaxies, gravitational collapse led to star formation, planetary systems, and eventually the conditions necessary for life to emerge and flourish. This progression from simple to complex challenges our assumptions about the nature of order and disorder. The second law of thermodynamics tells us that entropy, roughly speaking, disorder, always increases over time. Yet the universe's history reveals countless examples of local decreases in entropy. The formation of stars from diffuse gas clouds, the assembly of complex molecules from simple atoms, the evolution of life from non-living matter. These apparent contradictions resolve when we consider the universe as an open system, constantly expanding and cooling. The overall entropy of the universe continues to increase, but localized regions can experience dramatic decreases in entropy through the input of energy from their surroundings. Stars shine by converting nuclear potential energy into radiation, creating temporary islands of order in the cosmic sea of increasing disorder. The birth of the universe also illuminates the profound relationship between the very large and the very small. Quantum mechanics, originally developed to explain the behavior of atoms and subatomic particles, proves essential for understanding cosmic origins. The quantum fluctuations that gave rise to galaxy formation operated on scales far smaller than atomic nuclei, yet their effects shaped the largest structures in the observable universe. This connection between quantum and cosmic scales suggests a deep unity underlying all physical phenomena. The same principles that govern the spin of electrons and the emission of photons also determine the initial conditions for galaxy formation and the large-scale structure of space itself. In studying cosmic origins, we discover that the universe exhibits a remarkable consistency across all scales of size and energy. The question of cosmic origins also invites us to consider the nature of knowledge itself. Our understanding of the universe's birth comes not from direct observation. No human witness existed 13.8 billion years ago, but from careful inference based on current observations and theoretical reasoning. We reconstruct the cosmic past by studying the cosmic microwave background radiation, the abundances of light elements, the large-scale distribution of galaxies, and countless other astronomical phenomena. This process of cosmic archaeology demonstrates the power of human reason and imagination. Through mathematics and physics, we can reach back across billions of years to understand events that occurred under conditions more extreme than anything we can create in terrestrial laboratories. The fact that such reconstruction is possible at all suggests something profound about the relationship between mind and universe. between consciousness and the physical laws that govern reality. The study of cosmic origins also reveals the collaborative nature of scientific understanding. No single individual, or even single generation, could hope to unravel the complete story of the universe's birth. Instead, this knowledge emerges through the accumulated efforts of countless researchers, each contributing pieces to an ever-growing mosaic of understanding. From Einstein's insights into the nature of space and time to Hubble's discovery of cosmic expansion, from the theoretical work on Big Bang nucleosynthesis to the detection of the cosmic microwave background, our current picture of cosmic origins represents a truly collective human achievement. As we contemplate what the universe's birth teaches us about existence, we might also consider what it reveals about the nature of mystery itself. Despite centuries of scientific progress and increasingly sophisticated theories, the deepest questions about cosmic origins remain largely unanswered. We do not know why the Big Bang occurred when it did, or indeed whether the concept of when has any meaning in this context. We do not understand what, if anything, preceded the beginning of space and time. These persistent mysteries need not discourage us. Instead, they remind us that reality extends far beyond our current comprehension, that the universe contains depths of meaning and complexity that may forever exceed our grasp. The existence of such mysteries provides a sense of wonder and humility that enriches rather than diminishes our scientific worldview. The universe's birth also teaches us about the creative potential inherent in existence itself. From the simplest possible beginning, perhaps nothing more than quantum fluctuations in an abstract mathematical space, emerged all the richness and diversity we observe today. Stars and galaxies, planets and life, consciousness and culture, art and music and poetry. All of these arose from the fundamental creative impulse that initiated cosmic expansion 13.8 billion years ago. This creative principle continues to operate at every moment. New stars are being born in stellar nurseries throughout our galaxy. Planets are forming around young stars in distant solar systems. On Earth, evolution continues to generate new forms of life, while human consciousness creates new possibilities for meaning, beauty, and understanding. The universe's birth was not a one-time event, but rather the beginning of an ongoing process of creation that continues to unfold around us and within us. In the end, perhaps the most important lesson from cosmic origins is one of connection and belonging. We are not accidental visitors to an alien universe, but rather natural expressions of cosmic evolution. The same processes that formed galaxies and stars also formed the Earth and ultimately gave rise to life and consciousness. We are the universe becoming aware of itself, matter organizing itself into patterns capable of contemplating their own origins. This perspective offers both comfort and responsibility. We are part of something vastly larger than ourselves, connected through physical law and evolutionary history to every star in the sky and every form of life on Earth. Yet we also bear the unique responsibility of consciousness, the ability to understand, appreciate, and protect the remarkable cosmic inheritance that has been passed down to us through billions of years of stellar alchemy and planetary evolution. As we conclude our journey through cosmic origins, we find ourselves not at an ending, but at a beginning. The universe's birth story does not close the book on cosmic mystery, but rather opens it to new chapters of discovery and understanding. Each answer we uncover reveals new questions. Each solved puzzle points toward deeper enigmas waiting to be explored. The calm after creation is not the stillness of completion, but the quiet peace of ongoing wonder. In understanding how the universe was born, we gain not just scientific knowledge, but also a profound sense of our place in the cosmic story. A story that began 13.8 billion years ago and continues to unfold in every moment of our existence. I hope you enjoyed this journey through the origins of the universe. And if you're still awake, you'll find another fascinating space video right here on the screen. Until next time, and good night.